These are the largest construction projects America has ever attempted, billion-dollar builds that push engineering to its absolute limits. From record-breaking bridges to futuristic transit systems and sprawling city-sized developments, these megaprojects are reshaping the nation piece by piece. In this video, we uncover the United States' biggest megaprojects and the staggering scale behind the country's most powerful transformations. Sound Transit 3, often abbreviated as ST3, is a massive, multi-decade transportation infrastructure expansion project in the Seattle metropolitan region. It builds upon the earlier Sound Move and ST2 initiatives by significantly enlarging the regional light rail, bus, rapid transit, and commuter rail systems. The centerpiece of ST3 is over 60 miles of new light rail lines, which are being developed through phased construction efforts extending into the 2040s. The construction process begins with corridor identification, environmental impact studies, and community consultations. Engineers perform geotechnical surveys using boreholes and core sampling to understand subsurface conditions. Once the alignments are finalized, utility relocation takes place. This involves rerouting water, gas, electric, and telecom lines that intersect proposed trackways and stations. Earthwork follows with excavation and grading for at-grade segments, and tunneling operations initiated for underground portions. For tunnels, tunnel boring machines are deployed, often starting from launch pits constructed at key portal locations. These machines advance slowly, installing precast concrete segmental linings as they progress. For elevated rail, large-diameter drilled shafts and pile foundations support cast-in-place or precast segmental bridge spans. These elevated guideways are assembled using cranes and form travelers, depending on span length and urban constraints. Simultaneously, construction of maintenance bases and operation control centers is undertaken. These facilities are critical for housing rolling stock and coordinating train operations. Station construction is another vital component, with excavation, foundation pours, steel erection, and architectural finishes being executed in sequence. Many of these stations are designed to integrate with bus transit, biking facilities, and pedestrian infrastructure. Track lane includes concrete plinth or ballast track construction, depending on whether the line is underground, elevated, or at grade. Overhead catenary systems are installed for electric traction alongside signal systems, communication cables, and substations for power distribution. ST3 also includes major upgrades to existing infrastructure, which involves service interruption planning, night shifts, and temporary track diversions. Every step is overseen with rigorous quality control, safety protocols, and coordination with municipal agencies to minimize public disruption. Brightline West is a high-speed rail project under construction with the goal of connecting Las Vegas, Nevada to Rancho Cucamonga, California. Designed to reduce vehicle congestion on the I-15 corridor, the system is being engineered for electric trains capable of operating at speeds up to 200 miles per hour. The entire route spans approximately 260 miles and is being built primarily within the median of the I-15 highway, which presents unique logistical and structural engineering challenges. The first major phase of construction involves extensive right-of-way preparation. Since the alignment runs along an existing highway corridor, engineers must stabilize soil and regrade the median to accommodate double-track guideways. Excavation equipment is used to dig trenches and remove unsuitable soil, which is then replaced with compacted aggregate layers to form a solid base. Drainage systems are installed concurrently to prevent water accumulation and erosion beneath the future track. Concrete slab track construction is favored over traditional ballasted track due to its lower maintenance requirements and stability at high speeds. Precast or cast-in-place concrete track beds are laid with precision alignment to maintain tight tolerances for rail geometry. Continuously welded rail is installed atop these slabs using embedded fastener systems, which reduce vibration and noise while securing the rails rigidly. Bridge structures are required at various highway interchanges, flood zones, and wildlife crossings. These are built using deep foundations, such as driven piles or drilled shafts, with superstructures formed from precast concrete girders or cast-in-place box segments. Temporary falsework and heavy cranes are used extensively during this phase to hoist components into position. Stations are being designed with elevated platforms, intermodal access, and parking structures. Construction here includes deep excavation for utilities, elevator shafts, and escalator systems. Steel framing and curtain wall systems form the structural and architectural envelope of the terminals. Power delivery is achieved through an overhead catenary system. Substations convert utility power to the necessary voltage for high-speed traction. The catenary poles are installed at regular intervals with tensioning devices to maintain wire elevation and consistency. The Harbor Bridge project in Corpus Christi, Texas, is an extensive civil engineering effort focused on replacing the original through-arch bridge built in the mid-20th century with a modern, cable-stayed structure designed to meet 21st century transportation demands and navigational standards. The new bridge is engineered to span the Corpus Christi ship channel, allowing for increased clearance to accommodate larger cargo vessels entering the port of Corpus Christi while also expanding traffic capacity for roadway users. Construction began with the extensive groundwork necessary to support such a large-scale bridge. This included site clearing, utility relocations, and the construction of temporary access roads and work trestles. Deep foundation work was performed for the main towers, which support the cable-stayed spans. These foundations consisted of drilled shafts extending hundreds of feet into the soil and rock layers below, designed to support the enormous vertical and horizontal loads transmitted from the bridge deck through the cables and into the towers. The main span is being built using the balanced cantilever construction method. Precast concrete segments are fabricated off-site in a dedicated casting yard. Each segment is trucked to the site, lifted into place using specialized cranes or launching gantries, and then secured using high-strength epoxy and post-tensioning tendons. This method allows segments to be added symmetrically from each side of the tower, maintaining equilibrium and reducing the need for temporary supports in the shipping channel. The bridge's superstructure includes two massive pylon towers, constructed using slip-form techniques that allow continuous vertical casting of concrete. These towers rise to over 500 feet above the channel and anchor the array of stay cables that fan out diagonally to hold the deck in place. Each cable consists of multiple high-tensile steel strands, sheathed in protective coverings to resist corrosion in the coastal environment. On either side of the main span, long elevated approach viaducts are being constructed. These consist of precast or cast-in-place concrete girders supported on piers, which in turn rest on pile foundations. Road deck construction includes forming and pouring concrete slabs, installing parapets, expansion joints, drainage systems, and integrating lighting, traffic sensors, and barrier systems. When completed, the new Harbor Bridge will not only be an architectural landmark, but also a critical freight and commuter route engineered to last for over a century under dynamic traffic and environmental conditions. Empire Wind is a major offshore wind development located in the Atlantic Ocean off the coast of New York, aimed at delivering renewable energy directly into one of the most power-demanding regions of the United States. The project is being constructed in two phases, known as Empire Wind 1 and Empire Wind 2, together comprising several gigawatts of capacity. The wind farm is situated in the New York Bight, in a federally designated wind energy area stretching between 15 and 30 miles south of Long Island. The engineering scope of this project is immense, involving marine logistics, heavy structural fabrication, subsea electrical installation, and coastal infrastructure upgrades. Construction began with extensive marine geophysical and geotechnical surveys to assess the ocean floor. These surveys utilized sonar and core sampling to determine sediment composition, load-bearing capacity, and potential obstructions. Based on the findings, monopile foundations were selected for the turbines. These are large steel cylinders, some over 30 feet in diameter and hundreds of feet in length, driven deep into the seabed to support the massive towers and nacelles. Pile driving is conducted using dynamic hammers aboard specialized jack-up vessels that anchor to the seafloor during operations. The wind turbines, each rated at over 10 megawatts, consist of a steel tower, nacelle housing the generator and gearbox, and 3 rotor blades, each longer than a football field. These components are pre-assembled at coastal staging areas and transported by heavy-lift installation vessels. Once at sea, cranes aboard these vessels lift and assemble the components in stages. First, the monopile, followed by transition pieces, then towers, nacelles, and finally blades. Each turbine is connected to an offshore substation via inter-array cables buried into the seabed using jet plows or cable plows. The substations transform the voltage and transmit power through export cables back to shore. These export cables, which are also buried to protect against anchors and trawling, make landfall at pre-engineered transition points. Onshore, electrical substations are constructed to receive and further convert the power before it enters the regional grid. These substations include switchgear, transformers, and reactive compensation equipment to manage voltage stability. Simultaneously, the operations and maintenance facility is built at the port, featuring docking facilities for crew transfer vessels, storage for spare parts, and remote monitoring systems to track turbine performance in real time. Every stage is synchronized for logistical efficiency, environmental compliance, and long-term operational resilience. The O'Hare 21 Terminal expansion is a transformative infrastructure initiative designed to reconfigure and modernize one of the busiest airports in the world, Chicago O'Hare International. This project includes the expansion of Terminal 5, the demolition and complete replacement of Terminal 2, and the construction of 2 new satellite concourses that will be connected via underground pedestrian tunnels. The goal is to increase gate capacity, enhance passenger experience, and integrate international and domestic operations more seamlessly through what will be called the O'Hare Global Terminal. The process began with the expansion of Terminal 5, where the terminal was extended westward to add over 10 new gates. The expansion required major structural modifications, including deep foundation work using drilled shafts to support new concourse areas and jet bridges. Steel framing was erected in phased segments, coordinated tightly with ongoing airport operations to prevent disruption. Precast concrete panels, curtain wall systems, and advanced HVAC installations were used to ensure energy efficiency and expedited construction. Parallel to this, extensive enabling work was initiated for the new terminal core. This involved utility relocation, demolition of old utility tunnels, and excavation for new underground infrastructure. The most logistically demanding component is the future global terminal, which will replace Terminal 2. This new terminal will be built over active airfield areas, requiring a complex system of temporary taxiway realignments, structural decking over existing utilities, and phased demolition strategies to maintain uninterrupted air traffic operations. 2 new satellite concourses are being constructed west of the existing terminals. These concourses require pile-supported foundations due to the poor soil conditions and high groundwater table common to the site. Tunneling operations are underway to connect the new satellites with the main terminal. These tunnels are being bored using pressurized tunnel boring machines that install precast segmental linings as they advance, maintaining ground stability and controlling settlement risk near active runways. Each new terminal and concourse includes integrated baggage handling systems, advanced security screening infrastructure, and provisions for automated people mover expansions. Electrical systems are built with redundant power feeds, backup generators, and modern fire protection systems. The roofing structures are designed with large-span steel trusses to create open, column-free interior spaces, which are then fitted with custom architectural finishes reflecting local cultural themes. Throughout all phases, construction scheduling is meticulously planned using building information modeling and 4D sequencing to coordinate trades, manage passenger flow, and align with federal aviation security protocols. This expansion will not only increase the airport's capacity, but also completely redefine its functionality and resilience for decades to come. The 2nd Avenue Subway Phase 2 is the continuation of one of the most complex urban tunneling and mass transit expansion projects in the United States, aimed at extending the Q line from 96th Street to 125th Street in East Harlem. This phase includes approximately 1.5 miles of new twin-track tunnels and the construction of 3 new underground stations at 106th Street, 116th Street, and 125th Street. The engineering challenge is immense due to dense urban development, existing subsurface utilities, aged infrastructure, and the need to maintain uninterrupted city function during all phases of construction. The process begins with utility relocation, which is the most invasive and critical early task. Engineers must identify, reroute, and in some cases temporarily suspend operations of numerous existing utilities, including water mains, gas pipelines, electrical conduits, steam lines, and communications cables. This operation requires trench excavation along the length of 2nd Avenue and adjoining cross streets, followed by the installation of new reinforced conduits and manholes while ensuring services remain live wherever possible. Tunneling for the new segments will be completed using tunnel boring machines, which will be launched from designated shaft locations likely near 105th Street. These machines operate by using a rotating cutting head to break through rock and soil, while a conveyor system removes the excavated material. Behind the cutting head, the TBM installs precast concrete lining segments to create a finished tunnel wall. The twin tunnels are typically about 22 feet in diameter, allowing for safe clearance and space for walkways, conduits, and ventilation systems. Station construction will be executed using both cut and cover and mining techniques. At 106th and 116th Streets, the stations will likely be built using a cut and cover method, which requires deep trench excavation and the installation of temporary decking to allow traffic above to continue. These station boxes will be heavily reinforced and include mezzanines, platform levels, elevator shafts, stairwells, and emergency egress corridors. At 125th Street, due to geological and urban constraints, the station will be excavated using sequential excavation methods, where controlled blasting or mechanical excavation forms chambers and galleries that are immediately supported with shotcrete and rock bolts. New entrances, traction power substations, and ventilation facilities are also part of the scope. Once structural work is complete, crews will install tracks, third rail, signal systems, communications wiring, and lighting. Interior finishes, including wall tiling, signage, and fare control areas, are added last. The project requires constant coordination between civil engineers, transit specialists, utility managers, and public agencies to deliver safe, modern infrastructure while working beneath one of the most congested cities in the world. The American Legion Bridge Replacement Project is a major infrastructure effort to replace the aging and overcapacity bridge that carries the Capital Beltway, Interstate 495, over the Potomac River between Maryland and Virginia. The original bridge, built in the early 1960s, is structurally deficient and functionally obsolete due to narrow shoulders, limited capacity, and decades of heavy use. The replacement project involves constructing a modern, wider span that increases capacity, incorporates managed toll lanes, and enhances resilience to future traffic demand and environmental conditions. The construction sequence begins with extensive site preparation on both riverbanks. This includes clearing land for construction staging areas, installing erosion control measures, and conducting geotechnical investigations. Boreholes are drilled along the riverbed and banks to determine subsurface conditions, which informs the design and placement of bridge piers and foundations. Based on these studies, deep foundations using drilled shafts or driven piles are selected to anchor the new structure into stable rock or dense soil layers below the river. To maintain traffic flow during construction, a phased approach is employed. The new bridge is constructed parallel to the existing one, with some segments being built incrementally to allow traffic to shift as work progresses. Temporary trestles and causeways are installed in the river to support construction cranes, concrete pumps, and material transport without disrupting river navigation. The new bridge design features multiple travel lanes in each direction, including high-occupancy toll lanes. The superstructure is composed of pre-stressed concrete girders or steel box girders, depending on span length and navigational clearance requirements. These girders are placed atop reinforced concrete piers that rise from pile caps anchored into the riverbed. Each pier includes icebreakers and scour protection to resist hydraulic forces and sediment erosion. Deck construction involves forming, reinforcing, and pouring cast-in-place concrete slabs with integrated expansion joints and drainage systems. Barriers, lighting, and intelligent transportation systems such as traffic cameras and electronic tolling gantries are embedded into the bridge infrastructure. Noise barriers and aesthetic elements are incorporated to meet community and environmental guidelines. Upon completion of the new bridge, traffic is shifted and the old structure is carefully demolished. This involves cutting and removing steel or concrete elements in segments, using barges and cranes to control debris and ensure environmental compliance. The final phase includes grading, landscaping, and restoring shoreline features impacted during construction, leaving a modern, safer, and more efficient crossing over the Potomac River. The Frederick Douglass Tunnel is a major infrastructure endeavor designed to replace the Civil War-era B and P Tunnel in Baltimore, Maryland, a critical bottleneck along the Northeast Corridor. The new tunnel will increase capacity, improve reliability, and allow for higher speed travel for both passenger and freight rail. It involves the construction of 2 new parallel rail tunnels, each approximately 2 miles long, designed for electric Amtrak and MARC trains, while also preparing the corridor for potential future upgrades. The construction process begins with preparatory work, including land acquisition, environmental remediation, and utility relocation. Due to the urban setting, crews must identify and divert existing sewer, water, and communication lines that intersect the future tunnel alignment. Extensive geotechnical investigations are carried out along the alignment, using boreholes and geophysical instruments to map subsurface conditions. These findings inform the selection of tunnel boring machine technology and the design of support systems for the tunnel lining. The primary construction method involves using large tunnel boring machines to excavate through a mix of soil and rock beneath West Baltimore. Launch shafts are constructed at staging areas, requiring deep excavations supported by secant pile walls or slurry wall systems to maintain soil stability. Once the shafts are completed, the tunnel boring machines are assembled in segments and lowered into place. As each machine advances, it excavates material which is conveyed back to the surface, while simultaneously installing precast concrete tunnel segments to form the permanent lining. Above-ground structures include a new West Baltimore station, portal structures at either end of the tunnel, and ventilation shafts spaced strategically along the alignment. Each tunnel bore includes track slab construction, overhead catenary systems for electric traction, signal conduits, emergency walkways, and fire life safety systems. These elements are built sequentially following tunnel excavation, requiring multiple specialized crews operating in coordination. To handle stormwater and groundwater intrusion, sump pits and drainage systems are integrated along the tunnel invert, with pumping stations to discharge water safely. Tunnel ventilation systems include jet fans and shafts to manage air quality and smoke extraction in emergency scenarios. Substations are constructed nearby to deliver traction power, linked by high-voltage feeders running through dedicated conduit banks. Once both tunnel bores are completed and internal systems installed, track is laid and aligned to tight tolerances to support high-speed rail operations. Extensive systems testing follows, including power supply validation, signaling integration, and emergency response simulations. Upon completion, the Frederick Douglass Tunnel will replace a nearly century-and-a-half-old choke point with modern, resilient infrastructure capable of supporting the Northeast Corridor's next generation of rail travel. Waterline Tower is a super-tall mixed-use skyscraper under construction in Austin, Texas, set to become the tallest building in the state upon completion. Rising over 1,000 feet, It is engineered to combine residential, office, hotel, and retail functions within a single vertical structure, making it one of the most complex high-rise builds in the region. The tower's footprint is situated adjacent to Lady Bird Lake, requiring careful geotechnical planning and foundation engineering due to its proximity to the water and variable subsurface conditions. The construction process began with site clearing, excavation, and the installation of deep foundations. Because of the tower's extreme height and slender profile, engineers opted for a mat foundation supported by drilled piers. These piers are bored hundreds of feet into stable bedrock, reinforced with high-strength steel rebar cages and filled with Tremy concrete. The mat slab above them is a multi-foot thick concrete platform designed to distribute the tower's vertical loads evenly across the pier array. Following foundation work, vertical construction commenced with the use of a high-capacity jump form system to cast the central concrete core. This core houses elevators, stairwells, mechanical shafts, and acts as the primary structural spine resisting lateral loads such as wind and seismic forces. The concrete used in the core is high strength, often exceeding 10,000 psi, and is poured in successive lifts to maintain structural continuity and construction pace. Around the core, a steel and concrete floor framing system is constructed floor by floor. Composite steel beams span outward from the core to perimeter columns, supporting metal decking over which lightweight concrete slabs are poured. Post-tensioning is employed in certain areas to reduce slab thickness while maintaining structural performance. Construction cranes anchored within the building's core assist with vertical material transport and are periodically climbed upward as the tower rises. The facade is composed of a high-performance curtain wall system with floor-to-ceiling glass, aluminum mullions, and integrated sun shading features. The curtain wall panels are pre-assembled and hoisted into place to accelerate enclosure and allow interior fit-out to begin on lower floors, while upper levels are still being built. Mechanical floors, typically located at intervals, house equipment such as HVAC chillers, pumps, electrical switchgear, and water tanks. These are acoustically and structurally isolated to minimize vibration and noise transfer to tenant spaces. The top of the tower includes tuned mass dampers and structural outriggers that tie the core to perimeter columns, increasing lateral stiffness. Overall, Waterline Tower represents an intricate orchestration of advanced engineering, material logistics, and construction management, executed under tight spatial constraints and ambitious scheduling within an active urban environment. The Sequoia Solar Farm is a utility-scale photovoltaic power generation facility designed to produce hundreds of megawatts of renewable energy in a desert environment. The project spans thousands of acres and involves the installation of hundreds of thousands of solar photovoltaic modules, arranged in meticulously engineered arrays to maximize solar capture and energy output across seasonal variations. Construction begins with extensive site grading and preparation, ensuring a level and stable surface to accommodate the massive racking structures. The native soil is compacted and sometimes augmented with imported fill or geotextile fabric in areas requiring enhanced stabilization. The first major task involves driving steel piles into the ground to serve as foundations for the solar racking systems. These piles are typically driven to depths of 8 to 12 feet using pile-driving rigs calibrated to maintain consistent verticality and spacing. The racking systems are either fixed tilt or, more commonly in this project, single-axis trackers. Single-axis trackers are mechanically driven systems that rotate the solar panels to follow the sun's movement throughout the day, increasing energy capture by 20 to 30% compared to fixed systems. Following racking installation, photovoltaic modules are mounted in strings, often composed of up to 20 panels per row. Technicians bolt each module to the racking frame and connect them using standardized plug-and-play wiring systems. These module strings feed into combiner boxes distributed across the site. From there, direct current electricity flows into centralized inverters, which convert it into alternating current suitable for grid use. Electrical cabling is routed in underground trenches that are excavated using trenchers or chain-driven trenching machines. These trenches are backfilled with sand or thermal backfill to ensure heat dissipation and electrical insulation. Medium voltage transformers are placed at strategic intervals and mounted on concrete pads to boost the voltage for transmission. These are connected to a substation located at the perimeter of the farm, which aggregates all power generated and steps up the voltage for injection into the regional electrical grid. To ensure efficiency and longevity, each component of the system, modules, trackers, inverters, and transformers, is monitored via a SCADA system. This system collects real-time performance data, enabling operators to identify underperforming strings, inverter faults, or shading issues due to dust accumulation. The entire farm is encircled with fencing and access-controlled gates, and interior access roads are constructed using compacted gravel to allow maintenance vehicles year-round access. Serving as one of the largest and busiest airports in the world, the Dallas-Fort Worth International Airport represents a vast and intricately planned transportation infrastructure. The original construction of the airport began with the selection and preparation of an expansive site straddling the cities of Dallas and Fort Worth, requiring extensive grading, drainage systems, and soil stabilization over thousands of acres. Earth-moving operations included the redistribution of millions of cubic yards of soil to establish level runways, taxiways, and terminal zones, while ensuring compliance with strict FAA airfield geometry standards. The runways, which are among the longest in the country, were constructed in multiple phases using layered pavement systems. These include a stabilized subgrade, cement-treated base, and several layers of high-performance concrete capable of withstanding repeated heavy aircraft loads. Each runway incorporates lighting systems embedded in the pavement for approach, edge, and touchdown guidance, connected via underground conduits to airfield lighting control stations. Parallel taxiways are designed for optimal aircraft movement efficiency, with concrete paving sections built using slip-form pavers for tight tolerances and surface uniformity. Terminal construction involved erecting multiple large-scale structures with steel-framed superstructures and curtain wall systems composed of aluminum and high-efficiency glazing. Each terminal is equipped with multiple gate positions, connected to jet bridges, and supported by mechanical systems such as baggage handling conveyors, passenger boarding controls, and HVAC systems designed for high occupancy and variable loads. Subsurface utilities and automated train tunnels were constructed simultaneously, using cut-and-cover and bored tunneling methods to ensure interterminal connectivity without interrupting aircraft operations. The airport includes a central utility plant, constructed with chillers, boilers, and thermal energy storage tanks to provide efficient heating and cooling across the entire complex. Electrical substations and emergency backup generators are integrated into the system for uninterrupted power supply to critical operations such as runway lights, security systems, and air traffic control. To support intermodal transport, extensive roadways, bridges, and parking structures were built using pre-stressed concrete beams and deck slabs. Toll plazas and access control points are integrated with ITS systems for real-time monitoring and traffic regulation. Continuous expansion projects include terminal upgrades, runway extensions, and the integration of sustainability features such as solar panels, stormwater retention basins, and energy-efficient lighting. From a construction and engineering standpoint, Dallas-Fort Worth International Airport is a constantly evolving megastructure requiring phased construction strategies, airside-landside coordination, and specialized materials and systems to support safe and efficient global aviation operations. Constructing an academic building in the dense urban fabric of Manhattan presents challenges distinct from traditional campus development. The new academic building for the Fashion Institute of Technology had to reconcile limited lot dimensions, adjacent high-rise structures, and continual campus operations with the technical ambition of a vertically organized, highly specialized educational facility. From excavation to final systems commissioning, each stage of construction required precision scheduling, structural creativity, and adaptive coordination among trades. Foundation work commenced with site excavation, bounded by existing college buildings and street infrastructure. Due to space constraints, materials handling was tightly regulated with just-in-time delivery protocols and vertical staging. The site was prepared with soldier pile and lagging retaining walls to stabilize the excavation before the deep foundations were installed. Given Manhattan's bedrock proximity, drilled shafts socketed into schist or spread footings on rock were employed, depending on the structural loading zones. The superstructure was framed using a reinforced concrete core combined with a structural steel skeleton, an approach balancing rigidity with floor plan flexibility. The core housed vertical circulation, bathrooms, and utility risers, cast in sequence to maintain construction momentum. The steel framing proceeded floor by floor, using mobile tower cranes erected within tight street setbacks. Fireproofing crews followed closely behind steel erection, applying spray-on materials in coordination with weather protection and enclosure installation. The building envelope emphasized energy performance and natural daylighting, incorporating high-performance curtain wall systems. These facades featured insulated glazing with low emissivity coatings, aluminum mullions with thermal breaks, and integrated solar shading elements. The installation of the curtain wall followed a sequential glazing process using swing stages and exterior lifts. Connections between the curtain wall and concrete slabs included thermal isolation pads and expansion joints to account for building movement and thermal cycling. Inside, the layout accommodated specialized spaces such as design studios, lecture halls, fabrication labs, and exhibition areas. Floor structures were reinforced and acoustically isolated in zones requiring heavy equipment or high sound attenuation. Interior partitions used cold-formed metal framing and high-density gypsum board, often layered with acoustic insulation or resilient channels in areas adjacent to classrooms or performance spaces. Mechanical, electrical, and plumbing systems were designed with adaptability and energy conservation in mind. Air handling units were located on mechanical floors and rooftop penthouses, serving variable air volume zones controlled by digital building management systems. Exposed ductwork in select areas supported the industrial aesthetic of design education environments while maintaining accessibility for maintenance. Hydronic heating and chilled water loops were integrated into the slab structure in certain areas, supporting radiant temperature control. Lighting design utilized daylight-responsive LED fixtures networked into a centralized control system. Occupancy sensors, dimming controls, and programmable lighting scenes provided both energy efficiency and flexible ambiance suited for different academic tasks. Electrical panels and communication rooms were distributed vertically in stacked risers, with horizontal branch wiring routed through raised floors or suspended trays to simplify future reconfiguration. Final commissioning included HVAC balancing, system testing, emergency power simulation, and fire alarm integration. With its vertical organization, modern utility core, and adaptive lab spaces, the FIT academic building reflects a technically intricate approach to education infrastructure, delivering high-performance functionality within the vertical constraints of its Manhattan environment. Construction of the Brightline West high-speed rail begins not with rails, but with an extensive corridor preparation effort stretching along the Interstate 15 right-of-way between Southern California and Las Vegas. The alignment was selected to leverage existing transportation corridors, minimizing environmental impact while reducing the need for new land acquisition. Survey teams marked out the route using GPS-based geolocation, after which clearing and grubbing crews removed desert vegetation and leveled the alignment in preparation for subgrade construction. Due to varying soil conditions, crews implemented soil stabilization techniques such as cement treatment and moisture conditioning to achieve the compaction required for long-term settlement resistance. The rail substructure comprises several layers, beginning with compacted subgrade, followed by engineered fill, and a layer of ballast in zones where traditional track is used. However, in high-speed segments, especially those reaching over 180 miles per hour, a concrete slab track system will be utilized. This involves pouring continuous reinforced concrete slabs with expansion joints and embedded fasteners designed to hold the rail in place with millimeter-level precision. These slabs are set atop geotextile membranes and drainage systems to prevent water infiltration and thermal heave. Bridges and viaducts form a critical part of the project, particularly where the line crosses over existing roadways or environmentally sensitive terrain. Precast concrete girders are transported via specialized haulers and lifted using high-capacity gantry cranes. Abutments and piers are constructed using drilled shaft foundations, with rebar cages tied on site and lowered into the shafts before concrete placement. In seismic zones, isolators and energy-dissipating devices are installed to ensure structural resilience during earthquake events. Catenary systems for electric power delivery require the installation of overhead contact system, poles spaced at precise intervals along the corridor. These poles are anchored in concrete footings and support tensioned copper conductors delivering 25 kilovolts AC. Power substations are built at strategic intervals, converting utility-scale electricity to the necessary specifications for the trains and feeding the system through switchgear and protection circuits. Stations are designed as intermodal hubs, integrating ticketing systems, security screening, vertical circulation, and baggage handling. Platform edge doors, vibration-damping structural slabs, and acoustically treated canopies are incorporated to ensure comfort and safety at high-speed boarding conditions. All systems are tied into a centralized traffic control center that uses fiber optic networks and redundant data links for command, monitoring, and dispatch. Brightline West aims to redefine regional travel by delivering a fully electric, high-capacity corridor built with exacting civil and systems integration standards tailored for American infrastructure.
The redevelopment of Terminal 1 at John F. Kennedy International Airport is a major aviation infrastructure initiative designed to transform the aging terminal into a state-of-the-art global gateway. Scheduled for completion in 2025, the new Terminal 1 will significantly expand capacity, modernize facilities, and enhance the passenger experience through a comprehensive overhaul of terminal architecture, airside and landside access, and critical systems. This $9.5 billion project is being constructed on the sites of the former Terminal 1, Terminal 2, and the former Terminal 3, requiring an intricate phased demolition and construction process to keep the airport operational throughout the redevelopment. The first major phase involved the demolition of old structures, including the entirety of Terminal 2. Given the operational context of an active airport, demolition was performed in a highly controlled environment. Work included asbestos abatement, removal of outdated mechanical systems, and structural dismantling carried out in sequenced zones to maintain safety and minimize impact on adjacent runways and taxiways. Materials were sorted for recycling and disposal, with concrete crushed on site for reuse as fill-in subgrade construction. Following demolition, site preparation included soil stabilization and grading across the expansive redevelopment footprint. The new terminal is built on a reinforced mat foundation system, consisting of deep piles socketed into dense subsoil layers to counter settlement and lateral loads. Pile caps and ground-level slabs were poured in stages, using high-strength concrete and admixtures tailored to airport-grade durability requirements. Ground improvement techniques, including vibrocompaction and surcharge preloading, were employed to stabilize, fill, and mitigate long-term settlement risks, especially in areas adjacent to active taxiways. The superstructure of the terminal is being constructed with a combination of steel framing and reinforced concrete cores. The design emphasizes long-span steel trusses in the main check-in hall and departure areas to allow for wide-open spaces without intermediate columns. These trusses are fabricated off-site and erected using crawler cranes during low traffic periods, coordinated with Port Authority and air traffic control to maintain safety. Reinforced concrete shear walls and elevator cores provide lateral stability and house the terminal's mechanical and vertical transportation systems. The new Terminal 1 will span over 2 million square feet, incorporating up to 23 wide-body aircraft gates upon full build-out. To accommodate this, the apron and aircraft parking areas are being reconstructed with concrete pavements rated for Group 5 and 6 aircraft. Subsurface drainage systems, fuel hydrant lines, and de-icing fluid containment infrastructure are being installed beneath the apron. Jet bridges, preconditioned air systems, and ground power units are integrated into each gate position to streamline aircraft turnaround operations and reduce emissions. The terminal building itself is designed with a high-performance facade using double-glazed curtain wall systems with low emissivity coatings and integrated sunshades. These systems not only reduce solar heat gain, but also create a visually open and naturally lit interior environment. Roof structures are insulated and built to accommodate photovoltaic panels, contributing to the terminal's sustainability goals. Inside, the passenger processing zones are being built with modular and flexible layouts. The check-in hall includes self-service kiosks, bag drop counters, and high-capacity conveyor systems feeding into a next-generation baggage handling system. This system uses automated sorters, inline explosive detection machines, and robotic diverters to ensure both security and efficiency. The departures area includes centralized security screening with advanced CT scanners and automated tray return systems. The terminal's concourses are being built to accommodate retail, dining, and lounge spaces along with circulation corridors. Structural framing is designed to allow flexibility for future reconfiguration, with raised floors in select areas to support changes in mechanical and electrical distribution. Passenger movement is facilitated by moving walkways, elevators, and escalators, while lighting, air conditioning, and signage systems are controlled by a centralized building management platform. Mechanical, electrical, and plumbing systems are distributed from dedicated utility rooms located in basement and rooftop levels. The HVAC system includes high-efficiency chillers, thermal storage tanks, and air handling units with demand-controlled ventilation. Plumbing systems are outfitted with leak detection, low-flow fixtures, and hot water recirculation pumps to reduce consumption. Electrical infrastructure includes dual power feeds from independent substations, backed by diesel generators and battery storage systems for uninterruptible power supply to critical systems such as air traffic communications, baggage handling, and security equipment. Landside access is being completely reconfigured as part of the redevelopment. This includes new roadways for private vehicles, commercial transport, and shuttle buses, along with expanded curbside drop-off and pickup zones. New parking structures are being built with integrated wayfinding, EV charging stations, and real-time space monitoring systems. Pedestrian bridges are constructed to link parking and transit hubs directly with terminal levels, allowing safe and efficient passenger flow across busy traffic zones.
Stretching across the coastal plains of Kennedy County, Texas, the Penuscall Wind Power Project showcases the application of large-scale renewable energy infrastructure in a challenging environment defined by soft soils, high humidity, and persistent coastal winds. The construction process begins with extensive site development, including topographical surveys, environmental assessments, and access road construction through otherwise undeveloped ranch land. These gravel roads must support the transport of extremely long turbine blades, tower sections, and nacelles, necessitating careful grading, compacted subbases, and wide turning radii for specialized transport vehicles. One of the primary engineering tasks in this project involves the foundation work for each wind turbine. The coastal soil profile, composed largely of silts and clays with varying moisture content, demands a foundation solution capable of resisting both vertical dead loads and dynamic overturning forces induced by wind. Each turbine foundation typically consists of a large circular reinforced concrete pad, often exceeding 50 feet in diameter and several feet thick, with a central pedestal rising above grade. The foundation is constructed after excavation, followed by rebar cage placement, anchor bolt installation, and a continuous concrete pour to ensure uniform curing and structural integrity. The turbine towers are delivered in multiple tubular steel sections, which are bolted together on-site using tensioned bolts and high-strength flanges. Erection is carried out using hydraulic or lattice boom cranes with lift capacities tailored to the height and mass of each tower segment. Each tower supports a nacelle, a housing unit for the generator, gearbox, and control electronics, which is lifted and mounted at heights reaching over 200 feet. Rotor assembly involves attaching 3 fiberglass reinforced blades to a central hub on the ground, then lifting the entire rotor assembly as a single unit and mating it with the nacelle. Electrical infrastructure includes the installation of underground medium voltage collection lines connecting each turbine to an on-site substation. These cables are buried in trenches with warning tape and sand bedding to prevent damage and ensure thermal dissipation. The substation steps up the voltage from around 34.5 kilovolts to transmission levels, often around 138 kilovolts, for integration into the regional grid. Control buildings house switchgear, protection relays, and SCADA systems that allow for remote monitoring and turbine control. Given the site's proximity to the Gulf of Mexico, the project incorporates several measures for corrosion resistance, including galvanization of structural steel, marine-grade coatings on exposed equipment, and sealed electrical enclosures. Turbines are fitted with lightning protection systems that channel electrical discharge safely to ground, a critical feature in a region prone to frequent thunderstorms. Operational testing involves synchronization of the turbines to the grid, blade pitch calibration, yaw system checks, and vibration analysis to ensure balanced rotation. Once commissioned, the Penuscall Wind Power Project contributes hundreds of megawatts of clean energy, capitalizing on the consistent wind resources of the South Texas coastline, while demonstrating advanced construction sequencing and logistical planning in renewable energy deployment. At the heart of a massive urban revitalization effort, the Willets Point Soccer Stadium project emerges not only as a sports venue, but as a key piece of a complex redevelopment puzzle. Constructing a state-of-the-art stadium on a site formerly known for auto repair shops and contaminated soils involves far more than vertical construction. The first challenge is transforming the ground itself into a buildable foundation, a process requiring rigorous environmental remediation and extensive geotechnical preparation. Before any structural work begins, the site undergoes excavation of contaminated fill material, which includes petroleum-impacted soil and debris. Specialized crews follow a strict chain of custody protocol for soil sampling, segregation, and disposal. Remediation often involves the removal of several feet of surface material, followed by the installation of engineered fill and geotextile layers to cap and isolate any remaining residual contaminants. Groundwater treatment systems may also be installed to intercept and treat subsurface flow if hydrocarbon plumes are detected. Stadium construction begins with deep foundations, which are essential due to the site's prior use and potentially unstable subsurface conditions. A combination of drilled shafts and auger cast piles are used, designed to transfer loads through weaker upper strata into competent soil or rock layers well below grade. These piles are tested with static and dynamic load tests to confirm bearing capacity before concrete pile caps and grade beams are formed to create the structural base. The superstructure consists of a structural steel frame, prefabricated in sections off-site and trucked in for assembly using heavy lift cranes. Each piece is set into position using bolted connections and moment frames, forming a rigid skeleton for the seating bowl and roof structure. The stadium bowl is composed of precast concrete risers supported by steel raker beams, allowing rapid installation while ensuring consistency in alignment and dimensions. Vomitories, stair towers, and elevator cores are cast in place using high-strength concrete, reinforced with rebar cages tied and inspected on site. Roof systems vary by design, but for a stadium in this urban context, lightweight cantilevered trusses often support ETFE panels or metal decking to provide coverage without excessive shadowing or bulk. The cantilevers require counterweights or tension cables anchored deep into the structure to manage wind loads and uplift. Drainage systems are integrated into the roofing and seating areas to divert stormwater into underground retention systems, complying with city runoff regulations. Interior spaces such as locker rooms, concession areas, and mechanical rooms are built out once the primary structure is weather-tight. MEP systems are installed in coordination with architectural finishes, with central plant systems located in below-grade spaces or adjacent utility buildings. Electrical distribution includes robust conduit networks for lighting, broadcast infrastructure, and stadium-wide Wi-Fi systems. The playing field itself is constructed with precision grading and layered subsurface drainage. A sand-based root zone supports natural grass or hybrid turf, depending on the final performance criteria. Subsurface heating and irrigation systems are installed beneath the field surface, connected to central control units to maintain optimal playing conditions year-round. Completing the stadium includes extensive public realm improvements, sidewalks, plazas, lighting, and transit integration, transforming what was once industrial backland into a civic gathering place built to host tens of thousands of fans in a structure defined by engineering discipline and urban transformation. Shifting focus to one of the most significant sports construction projects in recent American history, Allegiant Stadium in Las Vegas began with an enormous excavation effort to prepare the site just west of the Strip. The soil conditions required pre-treatment due to high water tables and loose granular fill. To stabilize the subgrade, contractors used deep soil mixing and installed wick drains to accelerate consolidation. Once the pad was secured, work commenced on the foundation, which incorporated hundreds of drilled piers and massive concrete footings to support the superstructure. The building's primary frame featured a combination of steel trusses and precast concrete components. One of the defining features of the stadium, the sweeping roof canopy, was enabled by a network of long-span steel trusses, each weighing several hundred tons. These elements were fabricated off-site and delivered in sequential shipments, where they were assembled using gantry cranes and specialized rigging equipment. The roof itself was a cable-supported ETFE system that demanded meticulous tensioning and anchorage precision to accommodate thermal movement and wind uplift. Inside, the seating bowl was configured with precast raker beams and vomitory walls, each piece carefully aligned to maintain sightlines and support tiered loads. The lower bowl was cast in place, while the upper levels were constructed using a combination of steel risers and precast planks. Mechanical systems were housed in interstitial levels between the concourses and integrated into the structure to reduce noise and vibration transmission. One particularly ambitious component of the project was the operable field tray. Designed to support natural grass for NFL games, the tray rested on a series of rails embedded in the foundation slab. It could be rolled in and out of the stadium using hydraulic motors and steel wheel assemblies, weighing several million pounds in total. This required structural coordination with the surrounding apron and subgrade drainage systems, which had to accommodate both static and dynamic loads without settlement. Facade construction involved a high-performance curtain wall system clad in black fritted glass and metal panels. Behind this outer skin, wind bracing and thermal barriers were integrated to manage the desert climate. Each section of the envelope was panelized off-site and installed via mobile cranes in a rapid sequence, closing in the building in time for interior finishes to commence. Allegiant Stadium represents a convergence of speed, scale, and innovation completed on a fast-track schedule that demanded round-the-clock coordination across hundreds of trade contractors.
The construction of the Intel semiconductor fabrication plant in Arizona, part of a multi-billion-dollar investment in domestic chip production, is a highly advanced industrial project that combines precision engineering, extreme cleanliness requirements, and massive mechanical and electrical infrastructure. Situated at Intel's existing Ocotillo campus in Chandler, this expansion adds new fabs to one of the most technologically sophisticated manufacturing sites in the world. The project supports Intel's strategy to enhance U.S. semiconductor capacity and resilience in the global supply chain, and involves the creation of highly specialized cleanroom space, support buildings, and utility systems capable of sustaining the rigorous demands of advanced chip fabrication. Site development began with large-scale excavation and grading to accommodate multiple large-footprint buildings, including cleanroom facilities, utility plants, and administrative structures. Subsurface conditions in the desert environment required over-excavation and replacement with engineered fill to achieve the uniform settlement and load-bearing capacity needed for precision manufacturing operations. Thousands of deep foundation elements, including auger cast piles and drilled piers, were installed beneath the fab buildings to isolate them from vibration and thermal expansion, both of which can interfere with nanometer-scale semiconductor production. Above the foundation level, a reinforced concrete mat slab was poured to provide a base for the fab. This slab required an extremely flat and level surface finish, with tolerances far exceeding those used in conventional construction. Specialized concrete mixes were used to control shrinkage and thermal cracking, with continuous placement operations and finishing conducted under tightly controlled environmental conditions. The superstructure of the semiconductor fab buildings was constructed using a combination of steel framing and reinforced concrete walls, designed to support the heavy mechanical loads and provide a rigid frame for the cleanroom environment. The cleanroom floors were constructed using raised access systems, which allow for the routing of process utilities, electrical conduits, and airflow distribution beneath the floor surface. These systems are supported by structural steel decks designed to limit deflection and vibration to imperceptible levels. One of the most complex aspects of the Intel fab construction is the integration of its process support infrastructure. Semiconductor manufacturing requires ultra-pure gases, deionized water, high-voltage electrical power, vacuum systems, and chemical waste handling, all of which must be delivered and maintained with absolute precision. Gigantic central utility buildings were constructed adjacent to the fab to house air compressors, chillers, scrubbers, water treatment systems, and gas cabinets. These systems feed into the fab through an intricate network of insulated stainless steel piping, double-walled chemical lines, and redundant electrical feeders, all routed through dedicated utility corridors and mechanical chases. HVAC systems for the fab are designed to maintain cleanroom conditions in accordance with ISO Class 1 to Class 5 standards, depending on the process zone. These systems involve massive air handling units that filter air through high-efficiency particulate air and ultra-low penetration air filters, delivering laminar airflow through the cleanroom ceiling. Air change rates are among the highest of any building type, and temperature, humidity, and particulate levels are continuously monitored and adjusted by automated building management systems. The cleanrooms themselves are modular in construction, with prefabricated panels used to form walls, ceilings, and integrated air plenums. Interior finishes are composed of non-shedding, electrostatically dissipative materials that resist chemical corrosion and minimize contamination risk. Workers must pass through multi-stage gowning areas, air showers, and decontamination chambers before entering these spaces, and construction crews must follow similar protocols during the fit-out phase. Electrical infrastructure is equally critical, as semiconductor fabs consume vast amounts of power with a need for extremely reliable delivery. On-site substations, switchgear, uninterruptible power supplies, and emergency generators are installed in layered configurations to support continuous operation. Power quality is managed through real-time monitoring and conditioning systems to prevent voltage fluctuations or outages that could compromise sensitive fabrication tools. Process tool installation represents a major component of fab construction. These tools, which include photolithography scanners, etchers, ion implanters, and chemical vapor deposition chambers, are extremely sensitive and must be installed on vibration-isolated foundations with precise alignment. Tool hookup involves hundreds of connections for process gases, liquids, vacuum, and data communications. Each tool is commissioned individually and tested extensively before being certified for production. To manage water use, the site features a cutting-edge water reclamation plant that recycles process water for reuse in cooling towers and rinse processes. This system is critical in Arizona's arid climate and is one of the most advanced water sustainability efforts in industrial manufacturing. Waste treatment systems also neutralize and separate chemical byproducts for proper disposal, in compliance with federal and state environmental regulations. Construction was carried out using lean methodologies and building information modeling, enabling real-time coordination between trades and minimizing clashes between complex mechanical systems. Prefabrication was employed extensively for piping racks, electrical skids, and modular wall panels to accelerate installation and reduce site congestion. With thousands of workers on site daily, logistics were managed using zone scheduling, digital tracking, and real-time communication tools to maintain progress and safety.
The Southeast Connector project in the Dallas-Fort Worth region is a significant transportation infrastructure initiative designed to expand and modernize a key highway corridor to accommodate increasing traffic volumes and improve regional mobility. The construction process begins with detailed geotechnical investigations to assess subsurface conditions across the route. Boreholes and soil sampling guide the design of pavement structures and inform decisions about embankment stabilization, especially in areas with expansive clay or soft subgrades. Initial site work involves extensive utility coordination and relocation, given the presence of underground power lines, fiber optics, gas mains, and municipal water systems. Specialized crews use hydro-excavation and trenchless boring methods to install new utility runs without disrupting surface operations. Simultaneously, the construction zone is cleared of vegetation, existing pavement is milled or demolished, and temporary drainage measures are installed to manage stormwater during earthworks. Mass grading operations utilize GPS-guided bulldozers and scrapers to sculpt new roadway alignments, build embankments, and excavate cut sections through rolling terrain. In low-lying areas, wick drains and surcharge fills are employed to accelerate settlement and enhance long-term subgrade stability. Reinforced concrete box culverts and precast arch structures are installed to span creeks and drainage channels, with erosion control mats and riprap protection placed at inlets and outlets. The highway widening includes adding general-purpose lanes and managed lanes, which requires staged construction to maintain traffic flow. Temporary detours and traffic control devices are deployed in phases, with barrier systems, message boards, and flagging operations ensuring worker safety. Sub-base materials such as lime-treated soil or cement-stabilized base are placed and compacted before successive layers of hot-mix asphalt or continuously reinforced concrete pavement are applied. Bridges along the corridor are demolished and reconstructed with wider spans and higher clearances to meet modern standards. Foundation construction includes driven steel H-piles or drilled shafts depending on soil conditions, followed by the erection of cast-in-place or precast concrete bridge components such as abutments, piers, and girders. Superstructure placement is often conducted during overnight closures to limit traffic disruptions. Sound walls, intelligent transportation systems, lighting, and signage are installed in parallel with the mainline construction. Dynamic message signs, vehicle detection loops, and closed-circuit cameras are connected through fiber optic networks to regional traffic management centers. Upon completion of paving and striping, punch list activities address final grading, landscaping, and system testing before the project is opened fully to public use, significantly enhancing connectivity between southeastern Dallas and central Fort Worth. Revitalizing a historic waterfront facility for 21st century industrial and renewable energy needs, the South Brooklyn Marine Terminal presents a unique case study in urban maritime infrastructure development. Situated on the edge of New York Harbor, the terminal's redevelopment hinges on heavy structural upgrades, environmental remediation, and the integration of new logistics capabilities tailored to offshore wind, bulk cargo, and intermodal freight handling. The initial phase of transformation involves evaluating the structural condition of the existing waterfront bulkheads, piers, and yard surfaces. Many of these elements date back several decades and suffer from deterioration due to tidal action, saltwater corrosion, and lack of continuous maintenance. Engineers perform sonar surveys and underwater inspections to assess the condition of timber piles, concrete caps, and steel sheet piles. Based on these findings, repair or full replacement strategies are selected. In many areas, new sheet pile walls are driven, reinforced with tiebacks and anchor rods connected to landward deadmen buried beneath newly placed compacted fill. Yard space across the terminal is reconstructed with load-bearing capacity in mind. The goal is to accommodate heavy crawler cranes, nacelle transporters, and oversized offshore wind turbine components. Subgrade stabilization may include dynamic compaction or deep soil mixing to reinforce the ground, followed by layered gravel bases and heavy-duty concrete or asphalt paving systems. Drainage systems are upgraded in parallel to manage stormwater runoff and prevent pooling on wide open surfaces that span several acres. Maritime access upgrades include dredging the berth to maintain appropriate depth for deep draft vessels. Clamshell dredging techniques remove sediment under environmental oversight, with turbidity curtains deployed to minimize dispersion. Dredged materials are tested and either treated or transported to designated disposal or reuse sites. New fendering systems and mooring bollards are installed along the quay walls to support ships delivering wind turbine towers, blades, and monopiles. The redevelopment integrates electrical and data infrastructure into the terminal footprint, essential for handling modern logistics and power-intensive operations. High-capacity substations, switchgear, and underground conduit networks are installed to support lighting, crane operations, and refrigerated containers. Fiber optic cabling ensures real-time coordination of equipment and inventory, and integrated control systems allow remote monitoring of yard activity and vessel movements. To accommodate rail connectivity, existing track alignments are restored and upgraded with new ballast, ties, and signal systems, enabling seamless intermodal transfer between ship, truck, and rail. Rail spurs are aligned to serve warehousing and storage zones efficiently, reducing turnaround time for large or awkward cargo. Heavy lift pads and roll-on to roll-off ramps are constructed to handle self-propelled modular transporters and specialized trailers. Finally, the terminal is configured to serve as a staging hub for offshore wind development. This includes designated laydown areas for wind turbine components, reinforced assembly zones, and barge loading platforms. Specialized lifting equipment, such as pedestal cranes or self-erecting gantries, is permanently installed or brought in on a project basis. The combination of marine access, ground capacity, and logistics integration positions the South Brooklyn Marine Terminal as a cornerstone of regional industrial infrastructure, engineered to support both current freight needs and the future of clean energy deployment. Where a coal-fired power plant once dominated the landscape in Moapa, Nevada, the construction of the Reed Gardner battery storage system marked a shift toward clean energy storage and grid stabilization. The first phase of the project began with demolition and site remediation. Existing utility corridors, concrete pads, and buried infrastructure from the retired power plant had to be removed or repurposed. Soil testing and grading ensured that the land met the geotechnical requirements for placing a large array of battery enclosures and associated electrical equipment. Once the site was prepared, the foundation work proceeded with a modular strategy. Each battery container, typically the size of a shipping container, rested on reinforced concrete pads designed to bear static loads while allowing thermal expansion. These pads were poured with integrated cable trenches and embedded conduits for power and control wiring. The layout followed a linear alignment to optimize airflow, simplify maintenance access, and facilitate short routing to the power conversion systems. The energy storage units themselves consisted of lithium-ion battery cells housed in steel containers with integrated fire suppression, HVAC, and thermal monitoring systems. These containers arrived pre-assembled and were offloaded using mobile cranes or forklifts, then anchored in place with structural hold-downs. Adjacent to each group of battery containers, power conversion systems were installed, which included bidirectional inverters, transformers, and medium-voltage switchgear. These systems allowed the batteries to interface with the regional grid, converting stored DC energy into AC power during peak demand periods and drawing excess electricity during off-peak times. Cable terminations and system integration require detailed coordination. High-voltage AC and low-voltage control wiring were routed through separate underground duct banks to minimize interference. Grounding grids were installed beneath the entire array, bonded to each enclosure and system cabinet to ensure personnel safety and lightning protection. The site also included perimeter fencing, surveillance, and access control in compliance with NERC reliability and cybersecurity standards. A supervisory control and data acquisition system tied all battery enclosures, inverters, and transformers into a centralized control hub. Fiber optic links and programmable logic controllers enabled real-time monitoring of temperature, voltage, current flow, and system health. In addition to the core storage function, the installation featured black start capabilities and reactive power support to bolster grid stability during contingency events.
The Southeast Connector, officially known as the Southeast Connector Project, is a significant transportation infrastructure initiative located in Reno and Sparks, Nevada. Its purpose is to create a vital arterial roadway linking the southern and eastern regions of the Truckee Meadows area, improving regional connectivity, alleviating congestion, and supporting long-term economic development. The project spans approximately 5.5 miles and crosses environmentally sensitive wetlands, floodplains, and existing utility corridors. Its construction required an integrated engineering approach that accounted for hydrology, geotechnical stability, traffic flow, and environmental stewardship. The first phase of construction began with extensive site clearing and grading across the alignment, which traverses areas of previously undeveloped land, sections of the Truckee Meadows floodplain, and former military installations. To prepare the ground for heavy roadway infrastructure, over-excavation and recompaction were performed in areas with poor soil-bearing capacity. Geotechnical surveys identified zones requiring ground improvement, particularly in the marshy areas surrounding the northern end of the corridor. Ground improvement techniques included surcharging, wick drains, and the use of geotextile reinforced embankments to control settlement and increase subgrade stability. The roadway was built on a raised embankment for much of its length to prevent inundation during flood events and to allow for effective stormwater management. Structural fill material, including engineered gravel and crushed rock, was placed in compacted lifts to construct a stable road base. The roadway section includes multiple travel lanes in each direction, shoulders, bike lanes, and a multi-use path, accommodating both vehicular and non-motorized traffic. Median barriers, traffic signage, and roadway lighting were installed to enhance safety and visibility. One of the defining engineering features of the Southeast Connector is the number of bridges and culverts required to cross watercourses and wetland areas. The most prominent of these is the large bridge over the Truckee River, which required deep foundations using driven steel piles embedded into dense subsurface strata. The superstructure consisted of pre-stressed concrete girders and cast-in-place deck slabs designed to accommodate vehicular loading and seismic activity common to the region. Smaller bridges and box culverts were constructed at wetland crossings to maintain hydrologic continuity and allow for wildlife passage beneath the roadway. A central design consideration was floodplain interaction. The project corridor is situated in a basin that serves as a natural floodplain during extreme weather events. To mitigate flood risk and maintain flood capacity, engineers constructed large stormwater detention basins and conveyance channels adjacent to the roadway. These features are integrated with box culverts and drainage structures designed to manage runoff and attenuate peak flows. Hydraulic modeling was used to design these systems, ensuring that the new infrastructure would not adversely impact downstream properties or ecosystems. Extensive environmental mitigation and habitat preservation measures were integrated throughout the construction. The alignment required the relocation of sensitive species, the restoration of disturbed wetlands, and the preservation of existing vegetation where possible. Wetland mitigation included the excavation and grading of replacement wetland areas, installation of native plant species, and long-term hydrologic monitoring to ensure functional equivalence to the impacted habitat. Erosion control measures such as straw wattles, silt fencing, and temporary detention basins were deployed during construction to prevent sediment discharge into natural waterways. The project also involved the relocation and protection of existing utilities, including water mains, sewer lines, gas lines, fiber optic cables, and power transmission infrastructure. Coordinating these utility adjustments required phased shutdowns and rerouting, which were timed to minimize service disruptions. Underground utility corridors were constructed with reinforced concrete encasement in areas of high traffic loading, and all utility crossings were carefully coordinated with the vertical and horizontal alignment of the new roadway. Intelligent transportation systems infrastructure was incorporated into the design to support future traffic management and monitoring. This includes traffic signal controllers, vehicle detection sensors, overhead variable message signs, and camera systems integrated with the Regional Traffic Operations Center. These technologies allow for real-time traffic updates, incident response coordination, and improved safety for corridor users. Pedestrian and cyclist infrastructure was also prioritized. The entire length of the Southeast Connector includes a separated, paved, multi-use path designed for both recreational and commuter use. Grade-separated crossings and protective barriers enhance safety for non-motorized users. Trailheads with parking, lighting, and informational signage were developed at key access points, encouraging public use and improving community connectivity. Construction sequencing was managed to maintain local access, protect environmentally sensitive areas, and ensure continuous progress through seasonal weather changes. Major earthworks were scheduled for dry months, while bridge and drainage construction proceeded during cooler seasons with controlled dewatering and water quality monitoring. Daily inspections and environmental compliance reporting were conducted to maintain adherence to permits and minimize ecological impacts.
Situated in the heart of Southeast Texas's industrial corridor, the Golden Triangle Polymers project represents a major advancement in the Gulf Coast's petrochemical manufacturing capacity. This massive facility is being constructed to produce polyethylene and other polymer products from ethylene feedstock derived from natural gas liquids. The project begins with the development of a multi-acre greenfield site, requiring extensive earthwork, drainage management, and foundation preparation across terrain with high groundwater and soft, compressible soils. Soil stabilization techniques include the use of lime or cement treatment and surcharge fills to achieve acceptable bearing capacities for large process structures. Deep foundation systems are essential to support the heavy loads imposed by vertical vessels, reactor units, and compressor modules. Construction crews installed drilled piers and driven piles to depths exceeding 100 feet, with precision tolerances ensured through the use of GPS-guided rig systems and real-time monitoring during installation. Once foundations are completed, concrete pads and structural steel framing are erected to house process units such as cracking furnaces, separation columns, and polymerization reactors. These are built using modularized construction strategies, where large components are fabricated off-site, shipped by barge or heavy-haul truck, and lifted into position by crawler cranes with lifting capacities over 1,000 tons. The core production process centers around the ethane cracking furnaces, which convert ethane into ethylene through high-temperature thermal decomposition. These furnaces are complex assemblies of fireboxes, radiant tubes, and convection sections, all requiring precise refractory lining and thermal insulation. The resulting ethylene gas is rapidly quenched and routed to distillation columns where it is separated from byproducts under carefully controlled pressures and temperatures. Polymerization units downstream transform ethylene into polyethylene pellets through catalyst-induced chain reactions inside high-pressure reactors. These areas are designed with extensive piping, instrumentation, and control systems to maintain strict process parameters. Each reactor line is supported by a network of utility systems, including nitrogen generation, compressed air, cooling water, and steam distribution, all interconnected through color-coded pipe racks spanning hundreds of feet. Electrical power for the facility is delivered via high-voltage substations and switchgear buildings, incorporating redundant feeds and uninterruptible power supplies for critical control and safety systems. Distributed control systems and programmable logic controllers operate from a central control room, managing process sequencing, alarms, and interlocks. Fiber optic networks connect instrumentation throughout the site to provide real-time monitoring and diagnostic capabilities. A significant part of the construction effort is dedicated to environmental compliance and emissions control. Flare systems, vapor recovery units, and wastewater treatment plants are installed to capture and process effluents, ensuring the plant meets federal and state environmental standards. Additionally, fire protection systems, including foam suppression, hydrants, and emergency deluge zones, are integrated throughout the site to mitigate risks associated with flammable materials. Upon completion, commissioning and startup procedures involve comprehensive testing of mechanical systems, loop checks of instrumentation, safety interlock validation, and initial product runs under controlled conditions. The Golden Triangle Polymers project, once operational, will stand as a cornerstone in the region's industrial landscape, combining large-scale chemical engineering with advanced construction practices and operational precision. Beneath the dense urban landscape of the northeastern United States, the Gateway program's Hudson River Tunnel project emerges as one of the most intricate and vital rail infrastructure undertakings in the country. At its core, the tunnel is designed to bolster the heavily trafficked Northeast Corridor by constructing new twin tunnels beneath the Hudson River, providing a long overdue supplement to the existing pair of century-old tunnels that currently operate at near full capacity. Construction begins with extensive geotechnical investigations to map out the subsurface conditions beneath both the river and the surrounding urban areas. This involves drilling boreholes, performing seismic refraction surveys, and collecting core samples to evaluate the composition and stability of the underlying rock and sediment. Because the Hudson River bed consists largely of soft silt and clay atop layers of glacial till and bedrock, tunnel boring machines must be selected and calibrated with these highly variable ground conditions in mind. Launching the tunnel drives requires the excavation of deep approach shafts on both the New Jersey and Manhattan sides. These shafts provide access for tunnel boring machines and serve as critical logistical hubs for removing excavated material and bringing in precast concrete segments. Due to spatial constraints, particularly on the Manhattan side, where active rail lines and dense development restrict movement, all construction staging and materials delivery must be meticulously coordinated to avoid disruptions to existing rail operations. Tunnel boring machines used in this project are earth pressure balance types, capable of maintaining face stability while simultaneously installing the tunnel lining. These machines advance gradually, segment by segment, using a rotating cutter head to excavate material, while hydraulically driven erector arms install curved precast concrete segments into a ring formation. These segments are tightly bolted and gasketed to form a watertight structure capable of resisting the intense pressures from both the river and surrounding soil. As the tunnel progresses beneath the river, constant monitoring systems are deployed to detect ground settlement, machine performance, and water ingress. These systems ensure that any anomaly is detected and mitigated before it can threaten the structural integrity of the tunnel or impact above-ground infrastructure. Ventilation and safety systems are gradually installed behind the boring machines, including emergency egress pathways, fire suppression conduits, and future cabling ducts for power and communications. Upon completion of boring, the tunnel interiors must be outfitted with track systems, traction power supply, signaling equipment, and drainage systems. Specialized crews install continuous welded rail on concrete ties, ensuring smooth and safe high-speed travel. The power infrastructure includes overhead catenary lines supported by rigid cantilever arms, interfaced with substations to provide consistent electrical feed to passing trains. Advanced signal systems, designed for positive train control integration, are installed to meet current federal safety standards and accommodate future automation capabilities. When a bridge reaches the end of its useful life, replacement becomes not just a matter of modernization, but of safety and resilience. This principle guided the reconstruction of the Tion Yoga River Replacement Bridge, a project set in motion to restore reliable vehicular connectivity across the river while improving structural standards and accommodating future load demands. The existing bridge, after decades of service, exhibited wear typical of aging steel and concrete structures exposed to freeze-thaw cycles, road salt, and high water events. One of the most logistically demanding elements of the Las Vegas Convention Center expansion was its integration with an active facility that could not afford operational downtime. The construction team had to carefully phase demolition, excavation, and vertical build-out around major events and conventions, often working night shifts and off hours to avoid disruptions. The expansion project added more than 1 million square feet of new space, including exhibit halls, meeting rooms, and circulation areas, requiring a steel and concrete structural system capable of spanning large, column-free zones. The foundation work began with deep excavation and pile driving, Given the loose alluvial soils common in the Las Vegas Valley, crews installed hundreds of auger-cast piles, each reinforced with steel cages and tremie-poured concrete. A thick mat slab was then poured over this foundation grid, embedded with conduits for electrical distribution and floor drainage systems. The use of high-strength concrete mixes with specific slump tolerances ensured uniform performance and reduced cracking across the massive floor plate. The superstructure utilized a composite framing system combining wide-flange steel beams and concrete floor decks cast over metal decking. This method provided both strength and speed, allowing trades to follow closely behind the steel erection teams. Tower cranes and mobile telescopic cranes hoisted beam segments and roof trusses into place. For the convention hall roofs, long-span trusses were assembled in staging yards and lifted in modular sections to minimize on-site welding and alignment complexity. Mechanical, electrical, and plumbing systems were designed with scalability and adaptability in mind. Overhead utility zones carried air handling units, fire suppression mains, and lighting circuits along open web joists. These zones were isolated for sound attenuation, using acoustic baffles and vibration isolators to prevent mechanical noise from disrupting presentations and exhibits. Air distribution was handled through a combination of high-volume diffusers and underfloor displacement systems, ensuring comfort across densely populated exhibit spaces. The facade was clad in curtain wall glazing, aluminum composite panels, and architectural fins designed to reduce solar heat gain while delivering a visually striking presence along the strip. Exterior systems were tested for wind and water penetration using mock-up assemblies before full-scale deployment. The entire expansion was tied into a building automation system, enabling real-time monitoring of energy use, HVAC status, and life safety systems across both new and existing facilities.
The Springfield Rail Improvements Project is a comprehensive transportation infrastructure initiative designed to enhance rail operations, vehicular traffic flow, and safety within the city of Springfield, Illinois. Located along the primary north-south corridor for freight and passenger rail in central Illinois, this project addresses long-standing issues related to at-grade crossings, traffic delays, emergency vehicle access, and community connectivity. It involves the realignment of rail lines, construction of new underpasses and overpasses, installation of modern signaling systems, and the development of consolidated corridors to better manage the coexistence of rail in urban environments. The core of the project is the consolidation of multiple existing rail corridors onto a single, upgraded alignment along the 10th Street corridor, which will serve as the main north-south route for both freight and Amtrak passenger trains. This realignment requires the relocation of tracks previously running along the 3rd Street corridor. As part of this shift, new double-track sections are constructed using continuously welded rail on concrete ties, supported by engineered ballast and subballast layers. Subgrade preparation involved excavation to remove unstable soil, replacement with select fill, and compaction to achieve the necessary bearing capacity and drainage properties. The new corridor includes improvements to the track profile, geometry, and elevation to ensure compliance with modern rail standards. Geometric design ensures proper curve radii, super elevation, and grade transitions, accommodating both high-speed passenger operations and heavy freight trains. Drainage systems, including French drains, culverts, and swales, are installed along the right-of-way to protect the track structure and minimize water infiltration. Grade separation is one of the project's defining features. Multiple new underpasses and overpasses are constructed to eliminate at-grade crossings, enhancing both safety and efficiency. These structures include roadway underpasses with retaining walls, bridge decks, and approach embankments. For underpasses, construction begins with temporary traffic rerouting, followed by excavation and the installation of shoring systems such as sheet piling or soldier pile and lagging walls. Reinforced concrete box culverts or beam and slab bridge decks are installed to carry rail lines over the depressed roadways. Bridge abutments are supported by deep foundations, typically drilled shafts or driven piles, depending on subsurface conditions. Concrete formwork, reinforcement, and pour sequencing are closely coordinated to maintain quality control and structural integrity. Stormwater detention basins and pump stations are added near underpasses to manage runoff and prevent flooding during storm events. Signal and communications infrastructure throughout the corridor is upgraded to include positive train control, wayside signals, automatic block signals, and grade crossing protection where crossings remain. Fiber optic cables are laid in conduits adjacent to the track structure, forming the backbone of the communication system. Signal houses are prefabricated and equipped with relay logic, batteries, and interface panels, enabling centralized traffic control and real-time monitoring of train movements. To minimize disruption during construction, much of the work is staged. Temporary shoe-fly tracks are built to divert rail traffic around active work zones. These detour tracks are constructed to full structural standards and include turnout switches, ballast, and signal integration to maintain continuity of operations. As permanent infrastructure is completed, trains are shifted onto the new alignment, allowing for the removal of old track and crossings. Environmental considerations are integrated into every phase of the project. Wetlands, drainageways, and wildlife habitats are assessed during design, with mitigation strategies implemented where impacts are unavoidable. Erosion control measures such as silt fencing, seeded slopes, and temporary sediment basins are deployed during earthwork operations. Noise and vibration studies are conducted, leading to the installation of sound walls and the use of ballast mats or resilient rail fasteners near sensitive receptors like residential neighborhoods or historic districts. Public engagement is also a central component, with ongoing coordination between city officials, the Illinois Department of Transportation, and the Federal Railroad Administration. Stakeholder meetings, community briefings, and property owner consultations ensure transparency and allow concerns about property access, construction impacts, and aesthetics to be addressed proactively. In many locations, enhancements to urban design are incorporated into the project, including landscaping, pedestrian pathways, lighting, and public art installations that reflect Springfield's cultural identity. The Springfield Rail Improvements Project also supports broader goals of regional transportation planning. By consolidating rail operations onto a dedicated corridor, the project lays the groundwork for expanded passenger rail service, including future high-speed rail connections along the Chicago to St. Louis corridor. It also facilitates improved freight logistics by reducing delays caused by vehicle-rail conflicts and allowing for higher throughput along a modernized rail line. Construction logistics are tightly managed, with detailed scheduling, traffic control plans, and safety protocols. Equipment staging areas, material stockpiles, and worker access routes are established to reduce interference with local traffic and maintain construction productivity. Work progresses in multiple segments simultaneously, leveraging different contractors and crews to meet project milestones while keeping disruption to the community at a minimum.
At the heart of downtown Austin, the Texas Capitol Complex Phase 2 represents a continuation of a multi-year development plan to expand and modernize state government infrastructure while respecting historical context. Construction activities begin with meticulous site logistics planning to accommodate the urban setting, including traffic control, pedestrian rerouting, and staging areas for heavy equipment within a dense government district. Selective demolition of outdated facilities and parking structures clears the way for excavation, utility relocation, and deep foundation work. Excavation reaches depths sufficient for multi-level underground parking and utility corridors. During this phase, crews deploy soil shoring systems using soldier piles and lagging or secant wall methods to ensure trench stability and protect adjacent buildings from settlement or vibration. Dewatering systems with sump pumps and well points are installed to maintain dry conditions during substructure construction. Concurrently, new utility infrastructure, chilled water lines, electric duct banks, and storm drainage systems are embedded in concrete-encased trenches. Structural concrete operations dominate the next phase, with mat foundations poured in multiple continuous placements to support new office towers. Tower cranes are erected early to facilitate vertical construction, hoisting rebar bundles, formwork panels, and precast components. Floor slabs are formed using a combination of post-tensioned and reinforced concrete techniques to optimize span lengths and reduce floor thickness. Core walls housing elevators, stairwells, and mechanical shafts are formed with slip-form systems to accelerate vertical progress while maintaining structural alignment. Above grade, architectural precast concrete panels are installed as part of the building envelope. These panels incorporate design motifs inspired by the adjacent capital and blend with the surrounding architectural aesthetic. Window systems include energy-efficient glazing and aluminum framing with integrated sunshades. Mechanical, electrical, and plumbing systems are integrated into each floor through overhead coordination with BIM modeling to avoid clashes and maximize efficiency in confined ceiling spaces. A key element of the project is the expansion of the Texas Capitol Mall, which introduces pedestrian green space atop underground parking decks. This requires careful waterproofing, drainage layering, and placement of structural soil to support landscaping elements. Trees, lighting, benches, and pathways are installed using detailed site plans to ensure ADA compliance and long-term durability. Interior finishes follow close behind structural completion, including raised flooring for cabling flexibility, modular wall systems, acoustic ceiling panels, and high-efficiency HVAC controls. Security systems, IT infrastructure, and life safety features are tested during commissioning. When completed, Phase 2 adds critical state office space, enhances connectivity through walkable corridors, and reinforces the ceremonial axis of the Capitol with modern construction methods and sustainable design. Bridges that span tidal rivers and serve both freight and passenger rail must meet an unusual combination of durability, flexibility, and navigational accommodation. The Livingston Avenue Rail Bridge, a vital crossing over the Hudson River between Albany and Rensselaer, is one such structure, and its planned replacement presents a complex interplay of structural engineering, river hydraulics, and transportation continuity. The existing bridge, over 100 years old, suffers from frequent mechanical failures and speed restrictions, necessitating a full reconstruction while preserving continuous rail service throughout the process. Replacing a movable bridge over an active waterway introduces immediate sequencing challenges. The new bridge will likely be constructed on a parallel alignment to the existing span, minimizing disruption to current operations and allowing much of the work to proceed concurrently. Temporary causeways or trestles may be used for construction access, but these must be carefully engineered to avoid interfering with river navigation and environmental constraints, particularly those related to tidal flows and aquatic habitat preservation. Foundation work begins with driving deep piles into the riverbed to support the new bridge piers. These piles must penetrate through layers of sediment and into competent glacial till or rock, requiring a combination of vibratory and impact driving techniques. In certain areas, drilled shafts or large diameter caissons might be more appropriate due to subsurface conditions or noise constraints. Cofferdams are erected around pier locations to dewater the site and allow for dry concrete placement of footing and pier cap structures. The new superstructure will be designed to accommodate both high-speed passenger and heavy freight trains, likely employing steel through girders or a deck truss configuration to balance strength and span length. Modern design codes require larger live load allowances, greater lateral wind resistance, and robust fatigue life considerations, particularly important given the bridge's expected daily use by Amtrak and other rail operators. The track structure will use continuous welded rails supported on precast concrete ties and ballast, all configured to allow smoother transitions over expansion joints and movable elements. A key feature of the Livingston Avenue Bridge is its movable span, traditionally a swing span. In the replacement design, a modern swing, bascule, or vertical lift span must be selected based on navigational requirements and clearance needs. This movable section will be driven by hydraulic or electromechanical actuators with redundant controls, backed by fail-safe locking systems and real-time monitoring instrumentation. The machinery rooms and operator houses must be integrated into the bridge profile while allowing access for maintenance and inspection. At the outset of the MSG Sphere's construction in Las Vegas, the most immediate challenge was establishing a foundation capable of supporting a structure unlike anything previously built. The sphere's extreme diameter, spanning over 500 feet, and height exceeding 300 feet, necessitated a ring of deep foundation caissons. These caissons, drilled dozens of feet into the caliche-laden desert subsoil, provided load-bearing support for the concrete mat foundation that would carry the entire dome. Crews installed dense rebar cages and tremi-poured concrete in segments, ensuring continuous integrity under the enormous compressive and lateral loads. The frame of the sphere was formed using a hybrid structural system combining concrete cores with an extensive steel diagrid shell. The steel members, many of them curved and custom fabricated, were craned into place with extreme precision. Each joint had to accommodate subtle geometric variances in the spherical curvature, requiring extensive use of laser surveying and point cloud modeling during assembly. The use of node connectors, each one custom engineered, allowed thousands of steel segments to interlock into a stable geodesic structure. Work progressed concentrically, rising from the base upwards, forming a self-supporting lattice that grew in stages toward closure at the apex. Internally, the complexity intensified. The sphere's defining feature, its fully immersive LED display surface, required a compound curved interior supported by catwalks and rigging systems hidden behind the paneling. This interior surface included more than 100,000 square feet of high-resolution LED panels. Engineers had to account for thermal expansion, cable routing, and precise angles of incidence for projection mapping and acoustics. To achieve truly immersive sound, an advanced beam-forming audio system was suspended behind acoustic mesh panels, calibrated to direct audio precisely to each seat using an array of over 100,000 speakers and transducers. Externally, the sphere's envelope was sheathed in an exoskeleton clad with LED modules designed for all-weather performance. These panels were mounted using modular aluminum frames anchored directly to the diagrid steel. Wind loading, thermal cycling, and desert dust all influenced the choice of materials and mounting systems. Throughout the build, access was achieved with a mix of suspended scaffolds, articulating lifts, and perimeter ring cranes. Construction sequencing had to account for limited laydown space and active coordination with surrounding infrastructure. With the Las Vegas Strip nearby, noise restrictions, traffic control, and night work all shaped how the project advanced. The MSG Sphere stands as a demonstration of digital architecture converging with structural audacity, where immersive entertainment dictated the blueprint from foundation to facade.
The related Santa Clara project is a major urban development initiative in Northern California, transforming a former landfill site near Levi's Stadium into a dynamic mixed-use district. Envisioned as a dense urban hub blending residential, commercial, retail, entertainment, and hospitality components, the project spans over 200 acres and represents a model of large-scale master planning, sustainable design, and complex site engineering. Given its scale and the geotechnical challenges of building on a capped landfill, the construction of related Santa Clara required significant groundwork before vertical development could begin. Site development began with environmental remediation and geotechnical stabilization. The site had a history as a municipal landfill, necessitating the construction of an engineered cap to seal the waste material and prevent leachate migration. This cap consisted of layers of compacted clay, geomembranes, geotextiles, and protective cover soils. Before any structures could be built, the cap was inspected, reinforced where necessary, and overlaid with an elaborate system of gas venting and groundwater monitoring wells. Methane gas mitigation was a critical component of the design, with horizontal collection pipes, vertical extraction wells, and passive venting systems embedded beneath proposed building footprints. Given the risk of differential settlement on such fill material, structural design strategies emphasize shallow, flexible foundations for low-rise buildings and deep pile-supported foundations for taller structures. Load-bearing elements were designed with settlement tolerances in mind, and slab-on-grade floors were decoupled from building frames using isolation joints and subgrade void forms. All utilities and infrastructure conduits were routed in flexible, jointed systems to accommodate ground movement, with multiple access points for maintenance and inspection. Horizontal infrastructure development was extensive, involving the construction of new roads, water mains, stormwater systems, and electrical networks. The street grid was laid out to prioritize walkability and multimodal access, with curbless shared streets, wide sidewalks, and dedicated bike lanes. Stormwater management relied on a network of bioswales, underground detention vaults, and permeable pavements, designed to meet stringent regional stormwater discharge regulations while promoting on-site infiltration and groundwater recharge. One of the most complex components of the project was the construction of a central utilities plant and microgrid. This facility provides heating, cooling, and electricity distribution across the entire development using a district energy model. Chillers, boilers, thermal storage tanks, and backup generators are housed in a central structure connected to a network of underground utility corridors. These corridors carry chilled water, hot water, and electrical conduits throughout the site, reducing the need for decentralized mechanical systems and improving energy efficiency at scale. As vertical construction commenced, buildings were erected using a range of framing systems tailored to their use and height. Mid-rise residential buildings typically used post-tensioned concrete podiums supporting wood-framed or light-gauge steel superstructures, while office towers and hotels employed structural steel or reinforced concrete frames with shear walls and lateral bracing. Floor slabs were designed for flatness and serviceability, with embedded sleeves and core-drilled openings to accommodate MEP installations. Facade systems across the development included high-performance glazing, precast concrete panels, metal cladding, and fiber cement rain screens, all selected for durability and aesthetic variety. Building envelopes were constructed with continuous insulation, air barriers, and vapor retarders to meet California Title 24 Energy Code requirements. Roofs were equipped with reflective membranes, green roofing elements, and photovoltaic arrays tied into the site-wide energy monitoring system. Interior fit-outs varied depending on building type, but generally featured open-plan layouts with raised access flooring and modular wall systems in commercial spaces. Residential units were built with acoustic-rated wall assemblies, energy-efficient appliances, and low-flow plumbing fixtures. Retail shells were delivered with basic utilities stubbed to tenant spaces, allowing for customization during future tenant improvements. Open space and landscape architecture played a central role in the master plan, with a significant portion of the site dedicated to parks, plazas, and pedestrian corridors. Structural soil cells were installed beneath sidewalks to support street tree root growth and promote long-term canopy development. Irrigation systems used non-potable water sourced from a recycled water facility and monitored by smart controllers for efficiency. Public art installations, integrated lighting, and site furnishings were deployed to enhance usability and identity across the district. Transportation infrastructure included structured parking garages, transit shuttle drop-offs, and future-proofed provisions for autonomous vehicle integration. All parking structures featured EV charging stations, with conduits sized for future capacity increases. Bicycle storage rooms, lockers, and repair stations were incorporated into each block to support active transportation. Throughout construction, logistics were tightly managed to coordinate multiple contractors working across different zones. Site-wide scheduling tools, digital modeling, and construction sequencing simulations ensured that trades did not interfere with each other and that materials were delivered just in time. Erosion control measures, dust suppression systems, and noise barriers were enforced to minimize environmental impacts on neighboring communities and sensitive habitats along the nearby Guadalupe River corridor.
The Port Arthur LNG project is a large-scale liquefied natural gas development located along the Gulf Coast of Texas. This mega project, envisioned as a major export facility, encompasses multiple phases of complex engineering and construction efforts aimed at transforming raw natural gas into a liquefied state for overseas shipment. The process begins with site preparation, involving extensive clearing, grading, and compaction of coastal terrain to accommodate heavy infrastructure while ensuring stability against flood and storm surge risks common to the region. Soil stabilization techniques, including deep soil mixing and surcharge preloading, are employed to enhance bearing capacity for future foundation loads. Following site readiness, pile driving operations commence to support the foundations of cryogenic storage tanks, compression stations, and liquefaction units. These piles, typically made of steel or pre-stressed concrete, are driven deep into the subsurface to anchor against settlement and seismic activity. Simultaneously, massive underground utility corridors are excavated to house process piping, electrical conduits, and stormwater management systems. A key engineering challenge lies in the routing of high-pressure pipelines feeding the liquefaction trains, which must be precisely aligned and welded under strict tolerances to prevent leaks and ensure continuous flow. The core of the facility is composed of liquefaction trains, each comprising heat exchangers, compressors, gas turbines, and associated cooling systems. These units transform natural gas into LNG by progressively lowering its temperature to approximately minus 162 degrees Celsius. Modular construction techniques are often employed to fabricate components off-site and ship them to Port Arthur, where they are lifted into place using high-capacity cranes. This approach accelerates assembly and minimizes labor-intensive on-site fabrication. Adjacent to the process area, full containment LNG storage tanks are erected using a combination of pre-stressed concrete outer walls and inner nickel steel liners. These tanks require precise thermal insulation layers and boil-off gas recovery systems to manage pressure buildup. Marine infrastructure, including berths, jetties, and loading arms, is constructed along the shoreline to accommodate LNG carriers. This involves extensive dredging, pile-supported dock structures, and mooring systems designed to handle the thermal contraction of cryogenic loading arms. The project integrates advanced safety systems such as gas detection, emergency shutdown valves, and fire suppression networks. Electrical power distribution is established through substations and redundant backup generators, ensuring operational reliability. Finally, commissioning and startup testing involves systematic validation of all mechanical, electrical, and control systems before the terminal is certified for commercial export operations. Transforming one of the busiest transportation hubs in North America demands not only technical expertise, but a delicate balance of preservation, modernization, and uninterrupted operations. The Penn Station redevelopment is an undertaking defined by both its architectural ambition and the intense logistical complexity of upgrading a live rail facility buried beneath one of the most congested city blocks in Manhattan. The effort to overhaul Penn Station begins with structural enhancements below grade. The existing concourses, tracks, and platforms operate under the weight of multiple buildings, including Madison Square Garden. Any changes to circulation pathways, vertical access points, or mechanical systems must be executed within strict spatial constraints, often involving night and weekend work windows when train frequency is lowest. Structural engineers rely on advanced 3D modeling and building information modeling systems to coordinate the dense layering of utilities, columns, HVAC ducts, fire suppression systems, and passenger circulation zones. One of the first technical priorities is the relocation and upgrading of aging mechanical and electrical infrastructure. High-voltage feeds, signal cabling, and ventilation shafts are rerouted through newly created utility corridors designed to accommodate future capacity and ease of maintenance. These corridors often require underpinning of adjacent foundations and careful bracing to prevent soil movement during excavation. In several locations, jet grouting and soil freezing methods are used to stabilize the ground before deep cuts are made beneath active rail beds. At platform level, modifications target the improvement of passenger flow, accessibility, and egress capacity. New elevator shafts and widened staircases are inserted through cutouts in the existing slab, reinforced with steel framing and temporary shoring during the coring process. The platforms themselves are resurfaced with high durability, slip-resistant materials, and edge warning strips compliant with current accessibility standards. New wayfinding signage, audio systems, and tactile floor indicators are integrated throughout to improve user navigation and safety. Above ground, the redevelopment includes the construction of new headhouse structures that serve as public-facing entry points to the station. These involve excavation for new foundation systems, often using drilled shafts or micropiles to thread through dense subterranean infrastructure. Superstructures are composed of steel framing and glass curtain wall systems, engineered for maximum daylight penetration and designed to bear dynamic loading from foot traffic and potential roof equipment such as photovoltaic arrays or emergency generators. To address capacity and improve commuter experience, mezzanine levels are expanded, requiring significant reconfiguration of load-bearing elements. New concourses are built with post-tensioned concrete slabs suspended over active track beds using a sequence of cast-in-place pours and pre-assembled rebar cages. Work zones are isolated using sound and dust barriers, with negative pressure ventilation systems ensuring air quality for both workers and travelers. All construction phases are coordinated with rail operators and emergency services. Detailed construction staging plans sequence deliveries, waste removal, and equipment installation into narrow time slots between train operations. Emergency egress routes are continually maintained and adjusted as interior spaces evolve. The redevelopment culminates in a completely modernized Penn Station environment, mechanically efficient, structurally sound, and navigable at volumes exceeding several 100,000 passengers per day, executed entirely while the existing system remains in full operation. Unlike many arenas that rise from open space, the T-Mobile Arena in Las Vegas was constructed on a tightly constrained urban site, requiring deep logistical planning before the first shovel hit the ground. The initial site preparation involved extensive utility relocation, as existing storm drains, water lines, and power conduits had to be rerouted to accommodate the building footprint and its supporting infrastructure. With minimal laydown space available, construction sequencing was planned in detail to ensure materials arrived just in time for installation. The structural system relied on a hybrid steel and concrete frame. A reinforced concrete core formed the arena's vertical circulation spine and housed elevator shafts, stairwells, and mechanical risers. Around this core, a complex array of steel columns, raker beams, and trusses supported the sweeping roof and cantilevered seating decks. The roof was particularly challenging, as it required long-span trusses to bridge the open interior without intermediate columns, allowing unobstructed views from all seats. These trusses were lifted into place using synchronized crane lifts and were temporarily braced until lateral systems were completed. Within the bowl, precast concrete seating components were craned into position and set atop steel support members. The lower bowl was poured in place using cast-in-place concrete, allowing for integration of conduit chases and drainage systems directly into the slab. To ensure optimal acoustics, the interior envelope was lined with a combination of perforated metal panels and acoustic baffles, carefully arranged to diffuse sound energy and minimize echo. Mechanical systems were installed using vertical and horizontal distribution zones to maximize ceiling clearance and fan comfort. Chilled water plants, air handling units, and ductwork were located primarily above the event floor and distributed outward through high-level plenums. Special attention was given to integrating smoke control zones, emergency exhaust fans, and CO2 sensors into the overall HVAC design. Electrical systems featured redundant feeds, backup generators, and an extensive network of lighting control nodes to accommodate both performance and broadcast demands. The arena's exterior featured a curved facade made up of glass curtain wall, aluminum panels, and exposed structural elements. These were installed in phased sequences, using mast climbers and boom lifts to operate within the spatial limits of the surrounding development. Water infiltration protection was handled using rain screen design and perimeter sealant systems, ensuring long-term envelope integrity in the arid climate.
The O'Hare 21 Terminal expansion is a transformative aviation infrastructure program designed to reimagine Chicago O'Hare International Airport for the demands of 21st century air travel. At the heart of the program is the replacement and expansion of Terminal 2 with a new global terminal, along with the construction of 2 new satellite concourses and extensive modernization of existing terminal facilities. This multi-billion-dollar initiative involves complex phasing, advanced construction techniques, and tight coordination with airport operations to ensure uninterrupted service throughout the project's delivery. Site preparation began with the demolition of ancillary buildings, relocation of utilities, and reconfiguration of aircraft taxiways and service roads surrounding Terminal 2. Given the proximity to active runways and operational terminals, safety and logistics planning were paramount. Construction staging areas were established on airside and landside zones, complete with dust control systems, lighting, fencing, and noise monitoring. Crews implemented an array of protective measures to shield live taxiways, including jet blast deflectors, reinforced barriers, and safety exclusion zones. The replacement of Terminal 2 with the new O'Hare Global Terminals required complex foundational engineering to support a significantly larger and more structurally ambitious building. The substructure design utilized a grid of deep foundations composed of drilled shafts extending into glacial till and bedrock, with pile caps and grade beams forming the structural base. The mat foundation was poured in large segments with high-strength concrete using thermal control techniques to manage the heat of hydration and ensure structural integrity. The Global Terminal's superstructure consists of long-span steel framing, using massive plate girders and trusses to create column-free interior spaces for check-in, security, and baggage handling areas. The design required the prefabrication of structural steel assemblies off-site and timed delivery for erection using tower cranes and mobile lifting equipment. Steel members were connected using high-strength bolts and full penetration welds, with temporary bracing to stabilize the frame until the diaphragm action of the floor slabs was established. Curved roof geometry and soaring ceiling heights define the architectural vision for the terminal. The roof system uses a series of structural arches and purlins supporting metal decking and multiple layers of insulation, waterproofing, and reflective membrane roofing. Skylight assemblies, suspended from trusses, bring daylight into the terminal's core and were installed using swing stages and engineered rigging plans. The two satellite concourses are connected to the global terminal via underground pedestrian tunnels, constructed using cut-and-cover techniques and temporary earth retention systems. These tunnels house moving walkways, mechanical and electrical systems, and emergency egress paths. Utility corridors beneath the tunnels carry chilled water, fire suppression, data cables, and potable water piping from the central utility plant to each concourse. Terminal interiors are being built with modular construction techniques to allow rapid deployment and future flexibility. Raised access flooring systems provide underfloor distribution for power, data, and HVAC, supporting quick tenant turnover and reconfiguration. High-performance glazing systems are installed on the terminal facades to improve thermal comfort and reduce energy loads. These systems feature low emissivity coatings, thermally broken aluminum frames, and automated sunshades responsive to solar orientation. Mechanical, electrical, and plumbing systems are integrated into the terminal's core and distributed across vertical and horizontal chases. The HVAC design includes dedicated outside air systems with energy recovery ventilators, variable air volume units, and high-efficiency chillers linked to a central plant. The electrical backbone includes redundant switchgear, generator backup, and uninterruptible power supply units for critical systems such as flight information displays, security, and baggage handling. The baggage handling system spans the new global terminal and the satellite concourses, incorporating inline explosive detection screening, high-speed conveyors, and smart routing software. The system is built within a multi-level service zone and coordinated in detail using building information modeling to avoid clashes with structural and mechanical elements. Tilt tray sorters and destination-coded vehicle systems ensure rapid and accurate baggage movement across large distances. Airside infrastructure includes new aircraft gates with dual jet bridges, apron repaving, and reconfigured taxi lanes. Jet fuel hydrant lines are installed below the apron, connected to the airport's fuel farm via loop distribution mains. Each gate is equipped with ground power units, preconditioned air, and visual docking guidance systems, integrated into a digital apron management system that coordinates aircraft movements and turnaround operations. Passenger experience enhancements include expanded security screening zones with automated screening lanes, centralized customs and immigration processing, and intuitive wayfinding systems. Vertical circulation is handled through panoramic elevators, escalators, and stairs connecting multiple terminal levels. Concession and retail zones are constructed with pre-engineered kiosk platforms and coordinated MEP stubs, allowing rapid fit-out and tenant flexibility. Throughout construction, phasing and operational continuity are managed using detailed sequencing plans, temporary passenger corridors, and modular temporary facilities. Security zones are maintained with physical barriers, credentialed access, and 24/7 surveillance. All work must comply with Federal Aviation Administration regulations and be coordinated with the Transportation Security Administration and Air Traffic Control.
Rising prominently over the Corpus Christi ship channel, the Harbor Bridge Replacement Project represents a transformative upgrade to the region's transportation and maritime infrastructure. The effort to construct the new bridge begins with significant preparatory work, including clearing, grading, and establishing access roads for heavy machinery. Crews undertake extensive geotechnical surveys to design deep foundation systems that can safely support the towering cable-stayed structure in a coastal environment prone to high winds, corrosive salt air, and variable soil conditions. The core of the construction involves the installation of massive drilled shaft foundations. These are created using rotary rigs that bore deep into the substrata, often through layers of clay, sand, and limestone. Reinforcing steel cages are then lowered into the shafts and encased in concrete to form durable vertical supports. Given the location over navigable waters, temporary work platforms and marine barges are mobilized to provide access and material staging for overwater operations. The centerpiece of the bridge consists of two towering pylons that anchor the cable-stayed design. These pylons are constructed incrementally using a climbing formwork system that allows each concrete lift to cure before the next section is poured. Precision alignment is essential as the pylons must remain perfectly vertical over hundreds of feet of elevation. Once the pylons reach their full height, installation of the stay cables begins. These high-tension steel cables are anchored at the pylons and radiate outward in a fan-like array to support precast bridge deck segments. Deck segments are installed using a balanced cantilever method, where sections are added symmetrically from both sides of the pylon to maintain structural equilibrium. Each segment is carefully aligned and post-tensioned into place, forming the long-span roadway over the ship channel. Throughout this process, real-time structural health monitoring systems are employed to measure stress, displacement, and vibration to ensure safety and integrity during construction. The bridge approaches are constructed concurrently, involving the erection of elevated spans supported by precast concrete girders and pier caps. These components are assembled using cranes and falsework, followed by placement of the riding surface and expansion joints. The project also includes roadway realignments, upgraded interchanges, and the integration of pedestrian and bike paths to enhance multimodal accessibility. Upon completion, extensive commissioning activities verify all structural, electrical, and drainage systems. The new harbor bridge will provide significantly improved clearance for maritime traffic, greater traffic capacity for vehicles, and enhanced resilience against hurricanes and seismic events, marking a new chapter in regional infrastructure advancement. Laying an undersea transmission line is an operation that combines offshore engineering, marine geology, and high-voltage electrical infrastructure into a single continuous challenge. In the case of Empire Wind 1, the transmission system forms the backbone that delivers power from the offshore wind turbines to the onshore grid, spanning seabed, shoreline, and terrestrial corridors. The design and construction of this export cable involve multiple phases, each requiring distinct sets of equipment, expertise, and environmental management. The subsea cable installation begins with a detailed seabed survey. Hydrographic mapping, magnetometer readings, and geotechnical bore samples inform the alignment of the export route. The goal is to avoid boulders, shipwrecks, ecologically sensitive areas, and existing infrastructure like pipelines or fiber optic cables. Based on these findings, the route is finalized and cable protection measures are engineered, including burial depth profiles and potential use of rock berms or articulated concrete mattresses in harder substrates. Cable manufacturing is done well in advance, with the high-voltage alternating current cables fabricated in long, continuous segments. Each cable is composed of a central conductor, typically copper or aluminum, surrounded by layers of insulation, semiconducting sheaths, metallic armor, and external jackets. These cables are spooled onto massive turntables and loaded onto cable-laying vessels equipped with dynamic positioning systems to maintain exact alignment during installation. Prior to laying, a pre-trenching or plowing operation prepares the seabed. A remotely operated plow or jetting tool creates a narrow trench into which the cable is laid in a single pass. The cable-laying vessel then feeds the cable from its deck through a guide chute while maintaining precise tension and layback control. In areas where burial is not possible, post-lay protection using rock placement or concrete mats is deployed to prevent damage from anchors or trawling. At the landfall interface, a horizontal directional drilling method is used to bring the cable on shore without disturbing the shoreline or sensitive coastal environments. A borehole is drilled from an onshore pit out to the near-shore seabed, where a receiving pit or offshore transition joint bay is located. A duct is installed through this borehole, and the cable is pulled through using a winch system, creating a continuous sealed connection from sea to land. Onshore, the cable transitions from marine-grade insulation to terrestrial specifications at a cable transition joint housed in a secure underground vault. From there, the cable continues along a buried conduit route to the onshore substation, which is often newly constructed or significantly expanded to handle the incoming capacity. The substation includes transformers, switchgear, reactive compensation equipment, and grid interconnection systems. High-voltage transformers step the transmission voltage to a grid-compatible level, while harmonic filters and reactive power equipment stabilize voltage and frequency. Commissioning of the transmission system includes extensive high-voltage testing, thermal modeling, and live energization sequences. Protective relays and fault detection systems are calibrated to ensure the system can isolate any short circuits or overloads. Once operational, the Empire Wind 1 transmission line functions as the vital conduit converting offshore wind energy into urban-scale electricity supply, delivering clean energy while showcasing the precision and coordination demanded by subsea electrical engineering. In the vast and rugged terrain of western Nevada, the Greenlink West transmission line project began with a series of extensive environmental and geotechnical surveys. This corridor, stretching hundreds of miles, demanded careful route selection to avoid sensitive habitats, archaeological sites, and unstable soil zones. Once the alignment was finalized, crews mobilized with access road grading as the first priority. In remote desert areas, temporary haul roads and helicopter pads were established to enable movement of personnel, equipment, and materials to tower sites that had no existing access. Tower foundations varied depending on soil conditions. In rocky upland zones, foundation crews used blast hole drilling, followed by concrete anchors set deep into fractured bedrock. In softer or sandy valley floors, deep bored shaft foundations were poured with reinforced concrete, sometimes with steel casing to prevent wall collapse. Each foundation was designed to handle both axial and lateral loads imposed by conductor tension and wind shear on the towers. Concrete had to be batched locally or transported in rotating mixers across significant distances, requiring careful coordination to ensure consistency and curing integrity. The transmission towers themselves were largely lattice steel structures, fabricated off-site and delivered in sectional bundles. Erection crews used tracked cranes where terrain allowed, while in the steepest sections, helicopters were employed to lift tower segments into place. Ground crews then bolted the segments together using high-strength structural fasteners. Each tower was surveyed post-erection for verticality and alignment, using laser theodolites before conductor stringing began. Conductor installation involved multiple phases. First, pilot lines were pulled between towers using drones or helicopters. These were then used to draw in heavier steel messenger cables, which in turn pulled in the high-voltage conductor bundles. Each conductor was tensioned using hydraulic pullers and tensioners to exact sag tolerances specified in the design documents. Spacer dampers were installed at calculated intervals to prevent aeolian vibration, and insulators, often made from composite polymer materials, were mounted to separate the live conductors from the grounded towers. Substations on either end of the line required massive transformers, circuit breakers, and control systems to manage voltage conversion and grid integration. These substations were built concurrently, with site grading, pad installation, and bus work assembly proceeding, while the main line was being erected. The Greenlink West project not only involved transmission infrastructure, but also included communications fiber installation and SCADA integration for remote monitoring, forming a backbone for a more resilient and renewable-focused power grid across the region.
The American Legion Bridge Replacement Project is a critical infrastructure effort aimed at modernizing a key segment of the Capital Beltway, specifically the Interstate 495 corridor that spans the Potomac River between Maryland and Virginia. The existing American Legion Bridge, originally constructed in 1962, has long operated over capacity, experiencing severe congestion and structural fatigue due to increasing vehicular loads. The replacement project involves the complete removal of the aging bridge and construction of a new, expanded structure with improved capacity, safety, and multimodal functionality, all executed while maintaining active traffic flow across one of the busiest regional thoroughfares in the Mid-Atlantic. Construction begins with extensive preparatory work on both the Maryland and Virginia approaches. This includes widening the approach roads, relocating utilities, and constructing temporary service roads and retaining walls. Given the high traffic volume, much of this work occurs during off-peak hours with protective barriers and advanced traffic management systems deployed to safeguard workers and minimize disruptions. Intelligent transportation systems, including dynamic signage and real-time traffic monitoring, are established early in the project to maintain safe and efficient operations throughout construction. The new bridge is designed as a multi-span, pre-stressed concrete and steel girder structure with a substantially wider deck than its predecessor. It will accommodate additional general-purpose lanes, managed toll lanes in each direction, full shoulders, and a shared use path for pedestrians and cyclists. To support this expanded deck width, the new substructure includes larger piers and abutments constructed on deep foundations. Drilled shafts and driven steel piles are employed to reach load-bearing rock formations beneath the riverbed, with extensive underwater geotechnical investigations conducted to guide pile placement and sizing. Before the existing bridge can be removed, new bridge elements are constructed parallel to or in segments alongside the current bridge alignment. This phased construction approach minimizes the need for full closures, as traffic can be diverted to temporary bridge sections or shifted onto newly completed portions of the structure. Barges and temporary trestles are used to support materials transport and crane operations on the river, reducing dependency on land-based access and improving construction efficiency in the constrained corridor. The bridge superstructure consists of a composite steel girder and concrete deck system. Long-span steel girders are fabricated off-site, trucked to staging areas, and lifted into position using barge-mounted cranes and land-based crawler cranes. The girders are then spliced and secured using field welding and bolted connections. Once in place, the cast-in-place concrete deck is poured in sections, using form travelers and screeding equipment to ensure uniform thickness and surface smoothness. The deck is reinforced with high-strength steel rebar and includes post-tension tendons for enhanced performance under dynamic traffic loading. Drainage and expansion systems are integral to the bridge's durability. Deck drains, scuppers, and downspouts are installed to direct stormwater into collection systems without discharging directly into the river. Expansion joints and elastomeric bearings accommodate temperature-induced movements and vehicular loading, while corrosion-resistant materials and coatings are specified throughout to withstand de-icing chemicals and riverine humidity. The shared use path, located on the upstream side of the bridge, is physically separated from vehicular traffic and includes safety railings, lighting, and observation points. It connects to regional trail networks on both sides of the Potomac, enhancing non-motorized connectivity between Maryland and Virginia. The path structure is cantilevered from the main deck girders and supported with steel outriggers and braced frames designed for pedestrian loads and vibration criteria. Approach work involves realigning entrance and exit ramps, expanding merge lanes, and upgrading interchanges near the bridge termini. Retaining walls, noise barriers, and landscaping are constructed in tandem with grading and paving operations. Signal systems, gantries for toll lane management, and overhead variable message signs are installed and connected to regional traffic control centers via fiber optic networks embedded in conduit runs along the bridge structure. Environmental protections are implemented throughout the construction process. Silt curtains, turbidity barriers, and erosion control blankets prevent sediment from entering the Potomac River. Construction activities are scheduled to avoid sensitive spawning seasons for aquatic life, and work platforms are equipped with spill containment measures. The project also includes habitat restoration features such as riverbank stabilization and replanting of native vegetation along disturbed shoreline areas. Bridge lighting is designed to minimize glare and light pollution, using LED fixtures with shielded optics. Power and communication conduits are embedded in the deck to serve future upgrades in traffic technology and maintenance monitoring. The bridge is equipped with structural health monitoring sensors embedded in key components to collect data on strain, vibration, and temperature, allowing for predictive maintenance and long-term performance evaluation. Once traffic is fully shifted onto the new bridge, the original American Legion Bridge is dismantled in sections. This demolition process is executed using a combination of wire sawing, controlled explosive charges for superstructure removal, and mechanical dismantling. Steel girders and concrete components are removed by barge and processed off-site for recycling and reuse.
The Bay City Green Hydrogen Plant is an advanced industrial facility designed to produce hydrogen using electrolysis powered by renewable energy sources, primarily solar and wind. Situated in proximity to both energy supply corridors and industrial hydrogen demand centers, the project begins with extensive land development, which includes grading, drainage design, and geotechnical stabilization to support heavy equipment loads and ensure safe operation under varying environmental conditions. Electrical grounding systems are embedded in the foundational layout to protect sensitive electrolysis components from surges and lightning. Once the site is cleared and compacted, construction of the primary electrolysis units begins. These systems, typically using proton exchange membrane or alkaline electrolyzer stacks, require a precise mechanical and electrical assembly environment. Prefabricated skid-mounted modules are delivered to the site, each containing electrolyzer cells, transformers, rectifiers, and water purification units. These modules are set on reinforced concrete pads with embedded anchor bolts to withstand thermal cycling and mechanical vibrations. Deionized water feed systems are installed, incorporating reverse osmosis and filtration units to ensure electrolyte purity, which is critical for electrolyzer efficiency and longevity. Adjacent to the electrolyzers, a high-voltage substation is constructed to interface with renewable energy sources. This substation steps down incoming electricity from transmission voltages to operational levels suitable for the direct current systems feeding the electrolysis stacks. Power distribution infrastructure includes underground cable trays, switchgear enclosures, and load centers with automated fault detection. Battery energy storage systems are often co-located to buffer intermittent generation from renewables, smoothing out power supply fluctuations to maintain consistent hydrogen output. Hydrogen produced on-site is directed through stainless steel piping systems to compression units where it is pressurized for storage or distribution. These compressors are housed within sound-attenuated enclosures to meet regulatory noise limits and are equipped with redundant safety valves and blowdown stacks. Storage vessels, typically cylindrical tanks rated for several hundred bar, are constructed using high-strength carbon steel alloys and are fitted with pressure and temperature monitoring instrumentation. A control center oversees plant operations via a distributed control system that integrates sensors, flow meters, and programmable logic controllers. Real-time data acquisition enables operators to optimize electrolysis efficiency and respond to any anomalies. The plant also incorporates emergency shutdown systems, gas leak detection, and fire suppression equipment to meet industrial safety standards. Upon completion, commissioning involves a phased startup of each system, pressure testing of gas lines, calibration of instrumentation, and validation of control logic before the plant is cleared for continuous green hydrogen production. The replacement process began with a comprehensive assessment of hydrological patterns along the Tion Yoga River. Engineers conducted hydraulic modeling to determine the appropriate bridge height and span length that could withstand a 100-year flood event. River scour, which had contributed to undermining the older abutments, necessitated special attention in the design phase. To counteract this, deep foundation systems such as driven steel piles and reinforced concrete caissons were specified to anchor the substructure well below the scour depth. Construction sequencing had to be carefully planned to maintain traffic flow. In many such cases, a temporary detour structure or a stage construction method is adopted. Here, stage construction allowed half of the bridge to be built while traffic continued on the remaining half, supported by temporary shoring and reinforced decking. This minimized disruptions to local communities and commercial routes. Demolition of the old bridge structure required systematic deconstruction, starting with deck removal followed by segmental dismantling of girders and piers. Environmental controls were deployed to prevent debris from entering the river, including floating turbidity curtains and debris nets. Once cleared, work commenced on the new foundations, which included cofferdams constructed from interlocking sheet piles to isolate work zones from the water and create a dry workspace for excavation and concrete placement. The superstructure was designed as a multi-span steel girder bridge with composite concrete decking. High-performance weathering steel was chosen for the girders to reduce long-term maintenance by forming a protective oxide layer. The concrete deck was poured over galvanized stay-in-place forms, with integral shear studs to create a composite action between the steel girders and the concrete slab. Expansion joints and neoprene bearing pads were incorporated to accommodate thermal movement and live load deflection. The bridge rails and parapets were upgraded to meet current crashworthiness standards, employing reinforced concrete barriers with a steel rail on top. Drainage features were integrated into the deck design to channel water away efficiently, reducing the risk of icing in colder months. Roadway approaches were reconstructed with improved alignment and transition zones, incorporating guardrails, pavement striping, and signage to enhance driver safety. Throughout the project, geotechnical instrumentation monitored settlement and lateral movement, ensuring foundation integrity as loads transferred from the superstructure. Final inspections included load testing, visual surveys, and non-destructive evaluation methods such as ground-penetrating radar and ultrasonic testing of welds. Upon opening, the new Tion Yoga River replacement bridge represented not just a physical crossing, but a renewed commitment to infrastructure longevity and regional mobility, crafted through rigorous engineering and carefully managed construction logistics. Rising from the arid landscape of Story County, Nevada, the Gigafactory Nevada was conceived as a cornerstone of Tesla's ambition to revolutionize battery production at an unprecedented scale. Construction began with extensive earthworks to level the undulating terrain. The site, chosen for its proximity to rail lines and major highways, required vast quantities of excavation and grading. Bulldozers and graders reshaped the desert floor, while stormwater management systems were installed to direct runoff during rare but intense rainfall events. Once the pad was prepared, engineers focused on laying the foundation. Due to the immense footprint, eventually designed to exceed over 13 million square feet, the slab had to be poured in meticulously scheduled phases. Reinforced concrete was poured in segmented pours, each with embedded conduits and anchor bolts for future equipment. The structural frame was composed of prefabricated steel columns and trusses, delivered in sequenced shipments and lifted into place with crawler cranes. Crews worked in rotating shifts to maintain continuous progress, erecting hundreds of structural bays in parallel operations. Inside, the factory's layout followed a vertically integrated production flow. Raw materials entered at one end and passed through successive stages of battery cell fabrication, module assembly, and finally powertrain integration. To support this, the building's design included wide-span bays and a column-free floor plan for maximum flexibility. Utility corridors were embedded both overhead and beneath the slab to house compressed air, process water, chilled water lines, and high-voltage electrical conduits. HVAC systems were configured to manage precise temperature and humidity tolerances essential for lithium-ion battery production. In terms of energy use, the building was engineered to eventually operate on renewable sources. Roofing was structured to support photovoltaic panels, and internal systems were optimized for energy recovery and minimal waste. Fire suppression posed unique challenges due to the chemical nature of the materials. Thus, specialized foam systems and compartmentalized fire zones were integrated into the design. Construction logistics had to accommodate a remote site with limited access roads. Materials were staged off-site and trucked in with just-in-time precision to minimize storage on the congested site. Labor coordination was also a challenge, requiring thousands of workers from multiple trades and subcontractors, all operating under tight schedules and strict safety protocols. By scaling battery production to such a degree, Gigafactory Nevada marked a shift in how energy storage systems could be manufactured, economically, locally, and with the intent of creating a closed-loop supply chain.
The GreenLink West transmission line is a major electrical infrastructure project in the state of Nevada, designed to enhance grid reliability, support renewable energy integration, and increase transmission capacity across the western region of the state. Developed by NV Energy, this transmission corridor spans approximately 300 miles, connecting the Las Vegas area in the south to the Fort Churchill substation near Yerington in the north. The project represents a foundational component of Nevada's broader GreenLink Nevada initiative, intended to transform the state's electrical grid and facilitate access to clean energy resources while improving resiliency and operational flexibility. Construction of the GreenLink West project begins with detailed route planning and environmental assessment, as the alignment traverses vast expanses of public and private land, including Bureau of Land Management territory, tribal lands, and rural communities. Environmental permitting requires in-depth analysis of habitats, cultural resources, hydrology, and visual impacts. Once regulatory approvals are secured, fieldwork starts with land surveying, geotechnical borings, and the establishment of construction access routes. The transmission line itself is a high-voltage 525 kilovolt alternating current system using steel lattice towers and monopole structures, depending on the terrain and land use considerations. The design of the transmission line takes into account topography, wind loading, seismic considerations, and conductor sag. In mountainous areas, lattice towers are selected for their ability to span long distances and provide greater stability. While in open desert or agricultural zones, tubular steel monopoles are often preferred for their smaller footprint and faster installation. Foundation construction for each transmission structure is highly site-specific. In rocky or uneven terrain, drilled pier foundations are used, where holes are bored into the ground and filled with reinforced concrete. In softer soils, direct embed foundations or grouted steel shafts may be employed. Reinforcing steel cages are fabricated and placed on-site with concrete delivered by ready-mix trucks or mobile batch plants established along the corridor. Anchor bolts are set with tight tolerances to ensure the precise alignment of tower base plates. Tower erection involves lifting pre-assembled sections using crawler cranes, hydraulic booms, or helicopter lifts in remote or inaccessible areas. Each tower section is bolted together in sequence and alignment is checked at each stage. Conductor stringing follows tower installation and is conducted using tensioning and pulling equipment to carefully manage the weight and sag of the heavy aluminum conductor steel reinforced cables. Multiple phases of conductors are strung along with shield wires for lightning protection, and optical ground wires are installed to enable real-time monitoring and communications. Substations at each end of the GreenLink West line are upgraded or newly constructed to accommodate the increased voltage and new circuit paths. At these substations, high-voltage breakers, transformers, reactors, and switchgear are installed on reinforced concrete pads, protected by gravel surfacing and perimeter fencing. Buswork, insulators, and control cabling are arranged to allow for flexible operation and maintenance. And relay protection systems are programmed to detect faults and isolate them within milliseconds. To support future energy development, tap points and interconnection bays are integrated into the transmission design, allowing new solar, wind, and geothermal projects in central and western Nevada to tie directly into the grid. The transmission line is also engineered with N1 reliability criteria, meaning the system can continue operating even in the event of a single component failure, an essential feature for ensuring consistent power delivery in extreme weather or emergency conditions. Throughout construction, environmental mitigation measures are implemented to protect wildlife, water quality, and cultural resources. This includes installing erosion control barriers, wildlife exclusion fencing, and temporary bridging at stream crossings. Dust suppression is carried out with water trucks, and sensitive areas are avoided or monitored with environmental inspectors present during construction. When work is completed, disturbed areas are regraded and revegetated with native plant species to restore habitat and minimize erosion. Workforce logistics are a significant consideration given the remote nature of much of the route. Mobile staging yards, equipment laydown areas, and temporary access roads are established at intervals to support material delivery and worker access. Helicopter operations are scheduled to transport components and personnel to difficult-to-reach locations, especially in rugged mountainous zones where road access is limited or environmentally restricted. Digital construction management tools, including GIS-based routing systems, remote sensing data, and real-time construction monitoring platforms, are employed to coordinate crews, document progress, and track compliance with safety and environmental requirements. A central command center oversees construction phasing and coordinates with utility operations to avoid service disruptions and ensure synchronization with other grid infrastructure projects.
Towering above one of the busiest highway corridors in North Texas, the High-5 interchange in Dallas stands as a hallmark of multi-level interchange engineering. Built to replace a congested cloverleaf interchange where U.S. Highway 75 intersects with Interstate 635, the project required innovative design and construction techniques to manage complex traffic patterns while maintaining continuous vehicle flow through one of the region's primary transportation arteries. Initial phases began with detailed traffic modeling, utility mapping, and soil investigations to support the five-tiered structure's foundation. Given the depth of the lower roadways and the height of the upper ramps, foundation construction included the use of deep drilled shafts extending over 100 feet into the ground. These shafts were reinforced with heavy rebar cages and cast with high-strength concrete to support the significant vertical and lateral loads imposed by tall piers and long-span bridge decks. The interchange's construction was sequenced using a segmental approach, allowing multiple elevated ramps to be built concurrently with minimal interference to active lanes below. Crews used massive cranes to place precast concrete segments and steel girders at heights reaching over 120 feet. False work towers and temporary supports were utilized extensively to hold bridge components in place until post-tensioning systems were installed to lock the segments into structural integrity. Each level of the interchange demanded precise vertical and horizontal alignment, especially in the curved flyover ramps that must safely accommodate high-speed traffic. Bridge decks were formed using steel-reinforced concrete with epoxy-coated rebar to enhance corrosion resistance, an essential consideration in a structure exposed to both descent salts and Texas heat. Expansion joints, drainage inlets, and safety barriers were integrated during deck placement to ensure long-term durability and operational safety. Utility coordination was a major undertaking as numerous fiber optic lines, water mains, and gas lines crossed the construction zone. Relocation efforts required directional drilling, jack and bore methods, and trench excavation under tightly managed shutdown windows. In parallel, intelligent transportation systems were embedded, including dynamic signage, surveillance cameras, and real-time traffic sensors networked to regional control centers. Lighting, landscaping, and architectural detailing followed structural completion, contributing to the interchange's distinct urban identity. At full build-out, the High-5 interchange improved traffic capacity, reduced weaving conflicts, and significantly enhanced mobility for both regional and local drivers, all achieved through precise civil engineering, rigorous construction phasing, and innovative use of vertical space. Breaking ground on the new Las Vegas Stadium project involves an immediate confrontation with both scale and site complexity. Before construction on any vertical elements could begin, civil crews undertook mass grading operations across a site encompassing dozens of acres situated near critical transport infrastructure. Excavation equipment worked around the clock to balance cut and fill volumes, and sediment control basins were installed to comply with regional stormwater regulations. Soil stabilization techniques, including lime treatment and compaction grouting, were applied in zones identified by geotechnical surveys as having potential for settlement. The structural skeleton of the stadium is expected to be a composite of reinforced concrete cores and structural steel framing, optimized to support a multi-tiered seating bowl and a retractable roof or canopy. Temporary shoring towers and formwork systems will be deployed to construct the poured-in-place vertical cores, which will house elevator banks, mechanical risers, and egress stairs. Once the cores reach adequate height, sequential steel erection will begin. This involves the staged installation of primary steel columns, roof trusses, and raker beams, using crawler cranes capable of operating at tight radii due to the constrained urban site. Simultaneously, the substructure below grade will include utility tunnels, equipment vaults, and mechanical rooms. These require waterproofing membranes, concrete admixtures for sulfate resistance, and cast-in-place slab systems with embedded sleeves for mechanical and electrical penetrations. Mechanical engineers will be installing a central chilled water plant, routing large-diameter piping through below-grade trenches and into elevated concourses through a system of vertical shafts and distribution headers. The stadium's envelope will likely employ high-performance glazing, custom aluminum rain screen panels, and photovoltaic-ready roof surfaces. These components will be supported by secondary steel framing and sealed using multiple air and moisture barrier systems. Installation of the facade will proceed from multiple elevations concurrently, using mast climbers and suspended scaffold systems. Wind bracing and lateral load transfer connections will be closely monitored during this phase using field weld inspections and survey control points. Interior fit-out will be driven by overlapping trades working in tiered zones, beginning in back-of-house service corridors and proceeding outward to premium suites, concessions, and seating areas. Audio-visual integration, including massive LED boards, arena-grade speaker systems, and real-time data infrastructure, will require extensive cable tray systems and climate-controlled control rooms. The new Las Vegas Stadium will ultimately stand as a hyper-engineered fusion of sports architecture and logistical orchestration, delivering a landmark capable of hosting international events and enhancing the city's already iconic skyline.
The expansion of the Tesla Gigafactory in Austin, Texas, officially known as Giga Texas, represents one of the largest and most advanced industrial construction efforts in the United States. Located along the Colorado River on the eastern edge of Austin, the site spans over 2,000 acres and serves as a central hub for Tesla's vehicle manufacturing, battery production, and future operations related to its energy and robotics divisions. The expansion of this facility has required large-scale site development, precision engineering, and massive logistical coordination to accommodate the simultaneous construction of multiple production lines and infrastructure systems. Site work began with extensive earth-moving operations to level the vast tract of land and prepare it for heavy industrial use. Bulldozers, scrapers, and excavators were used to move millions of cubic yards of soil, creating a flat and stable platform for foundations. Drainage swales, detention ponds, and underground stormwater systems were installed early in the process to manage runoff and prevent flooding, especially given the site's proximity to the river and its location within a region subject to periodic heavy rainfall. Foundation work for the expanded areas of the Gigafactory involved deep excavation and the construction of reinforced concrete footings, grade beams, and mats. due to the sheer size and weight of the industrial equipment housed within the plant, including stamping presses, casting machines, and robotic assembly lines. Foundations were engineered to extremely tight tolerances. Concrete was poured in large, continuous placements using high-performance mixes designed for strength and durability. Reinforcing steel cages were pre-tied on-site and lifted into place using tower cranes, ensuring consistency and efficiency in the foundation builds. The superstructure of the Gigafactory expansion primarily consists of a steel frame system with large-span girders and open-web joists designed to create wide, column-free interior spaces. This framing approach allows for maximum flexibility in arranging production lines and material handling systems. Structural steel components were fabricated off-site and delivered in sequenced loads for immediate erection. Multiple cranes operated in parallel to lift and set beams, columns, and roof trusses, with crews bolting and welding connections at a rapid pace to maintain schedule. Roof and wall systems are built with insulated metal panels and reinforced concrete tilt-up walls. The use of tilt-up construction provided a quick and durable solution for enclosing the facility. Panels were cast on site in horizontal beds, then lifted into place using specialized rigs and temporarily braced until tied into the structural steel frame. The exterior envelope includes large format glazing, roll-up industrial doors, louvers for mechanical ventilation, and embedded systems for future photovoltaic arrays. Internally, the facility is divided into multiple production zones, including body in white, paint, drive unit, battery cell, and final assembly areas. Each zone is outfitted with an integrated mechanical, electrical, and plumbing backbone tailored to the specific requirements of the manufacturing process. Electrical substations, bus ducts, and motor control centers distribute power to equipment, while compressed air, chilled water, and process piping systems run throughout the structure in overhead utility racks. HVAC systems consist of large rooftop air handling units with variable air volume controls and ductwork engineered for high-volume ventilation. Battery and paint shop areas are served by specialized air filtration systems and climate control to maintain environmental conditions necessary for quality control and safety. Fire protection includes wet pipe sprinkler systems, foam suppression in high-risk areas, and a network of fire alarm panels and detection devices distributed through ceiling and wall cavities. One of the most critical components of the expansion is the battery cell manufacturing area. This section requires ultra-clean environments, achieved through the use of clean room standards and enclosed spaces, positive pressurization, and air filtration. Mechanical isolation, anti-vibration pads, and precision leveling are incorporated into the floor systems to support sensitive equipment like electrode coating machines and cell assembly stations. Material movement throughout the Gigafactory is supported by automated guided vehicles, overhead cranes, and floor-mounted conveyors. These systems are designed to move components and finished products between zones without interfering with human workflow. Logistics tunnels, high bay racking systems, and buffer storage areas are constructed to support just-in-time delivery and reduce operational bottlenecks. The facility's expansion also includes workforce amenities such as office space, cafeterias, training rooms, locker facilities, and employee parking. These support structures are built using conventional steel framing and modular interior finishes. Elevated walkways and observation decks allow management and visitors to safely monitor operations while minimizing interference with production. On the exterior, the expansion incorporates new access roads, loading docks, and utility corridors. Heavy-duty concrete pavements are laid for truck traffic and equipment transport, while perimeter fencing, lighting, and security systems are installed to maintain site safety. Landscape buffers and erosion control measures are implemented to minimize environmental impact and comply with regulatory requirements. The Gigafactory expansion is managed using advanced construction technologies, including building information modeling, 4D scheduling, and real-time project tracking. Construction crews work in multiple shifts to maintain continuous progress, with prefabrication and modular construction methods employed to accelerate timelines.
Perched high above the Colorado River, the construction of the Mike O'Callahan Pat Tillman Memorial Bridge required a level of structural precision and environmental coordination seldom encountered in highway infrastructure projects. Spanning nearly 900 feet across the Black Canyon, just downstream of the Hoover Dam, the project's location presented formidable challenges, including extreme elevation, rugged topography, high winds, and protected surroundings. The goal was to reroute U.S. Route 93 traffic off the Hoover Dam, necessitating a bypass bridge that could support heavy truckloads while enduring significant thermal and seismic forces. Foundation work began with the construction of vertical columns anchored into the canyon walls. These columns required deep rock sockets drilled into the solid bedrock on both the Nevada and Arizona sides. Blasting, rock bolting, and controlled excavation were used to establish working platforms and construct reinforced concrete footings. Once the columns were complete, temporary cable stays were strung across the canyon to support the next phase, the twin-rib concrete arch that would ultimately carry the bridge deck. This twin arch was built using a cantilever segmental method. Crews cast concrete segments outward from each canyon wall in balanced pairs, inching their way across the gap with the aid of a cable-supported highline system and traveling formwork. As each segment cured, post-tensioning tendons were tensioned internally to bind the structure and prevent shear or flexural failure. Each section was surveyed and adjusted using hydraulic jacks to maintain precise alignment as the arch legs advanced toward mid-span. Upon closure of the arch, deck construction commenced. Steel girders were lifted by cranes stationed on temporary towers and connected to the arch ribs through vertical spandrel columns. The bridge deck itself was a cast-in-place concrete slab, poured in sections with embedded rebar and expansion joints to accommodate thermal movement. Barrier rails, lighting systems, and crash protection were then installed along the deck edges. Wind and seismic design were paramount. The bridge incorporates tuned mass dampers and elastomeric bearings at key support points, allowing it to flex under dynamic loading without structural compromise. To ensure safety during construction, catwalks and harness points were anchored throughout the span, and workers operated under a highly regimented fall protection protocol.
The Port of Long Beach Middle Harbor Redevelopment Project is a large-scale maritime infrastructure initiative aimed at modernizing and consolidating two aging shipping terminals into a single, highly automated, and environmentally sustainable container terminal. Located within one of the busiest ports in the United States, the project enhances cargo handling capacity, operational efficiency, and environmental performance, positioning the Port of Long Beach as a global leader in port technology and green logistics. Spanning over 300 acres, the redevelopment required extensive dredging, land reclamation, structural upgrades, and the implementation of advanced terminal automation systems. The initial phase of the project involved the demolition of obsolete structures, including wharves, cranes, warehouse buildings, and paved storage yards. Asbestos abatement, utility disconnection, and hazardous materials removal were carried out before full demolition could proceed. Controlled demolition methods and water suppression systems were used to mitigate dust and environmental impact. Salvageable materials such as steel, concrete, and timber were sorted and recycled, aligning with the port's sustainability goals. Once the site was cleared, major marine construction began. The waterfront area underwent significant dredging to deepen the berths to accommodate post-Panamax and ultra-large container vessels. Dredging operations used hydraulic cutter suction and clamshell dredges, removing silt and sand to reach depths exceeding 50 feet. Dredged materials were transported to offshore disposal sites or used as fill for land reclamation elsewhere within the harbor. The berths were then reconstructed with reinforced concrete wharf structures supported by large-diameter cast-in steel shell piles driven deep into the subsurface sediments. Each wharf section was designed to support the next generation of ship-to-shore gantry cranes, requiring high-capacity pile caps and deck slabs with post-tensioned reinforcement. Fender systems, mooring bollards, and ship access ladders were installed along the quay wall, meeting international standards for vessel accommodation. The cranes themselves were mounted on embedded crane rails with power and data conduits integrated into the wharf edge, enabling fully electrified operation. Simultaneously, the terminal's backland area was regraded and compacted to create a uniform, high-strength surface for container storage, truck lanes, and support facilities. Paving was done using reinforced concrete designed for heavy axle loads. A network of subsurface utilities, including stormwater drains, electrical conduits, water mains, and fire protection loops, was installed below grade, coordinated through 3D modeling to avoid conflicts and streamline future maintenance. One of the hallmark features of the Middle Harbor redevelopment was the integration of automation technology into terminal operations. Automated stacking cranes, guided by a terminal operating system, were deployed in container yards. These cranes operate on fixed rails and are powered by electricity, dramatically reducing emissions and labor costs. Containers are moved between yard stacks and transfer zones, where manned or automated vehicles deliver them to and from ships or trucks. Positioning accuracy, collision avoidance, and task optimization are managed through centralized software, interfacing with container tracking systems and real-time data networks. The truck gate complex was also redesigned to support rapid processing and minimize idling. Optical character recognition, biometric verification, and license plate readers were installed to allow for automated identification and routing. RFID tags on containers and chassis enable seamless integration with the TOS, ensuring drivers are directed efficiently through the terminal. Queue management systems, electronic signage, and automated barriers improve safety and operational flow. The Middle Harbor Terminal was designed with an all-electric infrastructure to reduce its environmental footprint. This included electric cranes, yard tractors, and refrigerated container plug-ins powered by the terminal's shore-based electrical system. Ships docking at the terminal are provided with shore power connections, allowing them to shut down auxiliary engines and eliminate emissions while at berth. Substations and electrical vaults were strategically placed to distribute medium-voltage power throughout the terminal, while redundancy was built in to ensure uptime reliability. Stormwater management was another key environmental component. The redevelopment included construction of biofiltration basins, permeable paving in select areas, and underground detention systems to control runoff. These systems filter pollutants and reduce discharge volume into harbor waters. In addition, lighting systems were upgraded with LED fixtures and dark sky compliant shielding to minimize light pollution and energy consumption. Rail infrastructure was also upgraded to support near-dock intermodal capabilities. New tracks, switches, and crossovers were constructed to tie the terminal into the Alameda Corridor rail network, allowing for the direct transfer of containers between ships and trains without truck drayage. Rail-mounted gantry cranes service the on-dock rail yard, loading and unloading double-stack container trains efficiently while maintaining schedule flexibility. Construction was phased to allow portions of the terminal to come online, while other sections remained under development. Each phase included commissioning and testing of all systems, training of personnel, and calibration of automated equipment. Extensive coordination was maintained with the U.S. Coast Guard, Environmental Protection Agency, and local air quality districts to ensure compliance with safety and environmental regulations.